Why can't we see the edge of the universe? Imagine standing on a mountaintop with a telescope so powerful it could peer across the entire cosmos. You point it outward, eagerly scanning for the universe's edge. But no matter how far you look, no boundary reveals itself. Why? Is the universe infinite? Or is there something fundamentally strange about the nature of space-time itself? This question opens one of the greatest paradoxes in astronomy: the elusive edge of the universe. At first glance, the problem seems simple. If the universe had a beginning, shouldn't it have an outer limit? The Big Bang, the widely accepted theory for how the universe began, describes a single moment 13.8 billion years ago when everything, space, time, matter, exploded into existence. So, shouldn't that explosion have a frontier, a leading edge racing outward like a cosmic shockwave? Paradoxically, the answer lies in how the universe expands, not outward like a balloon inflating into a larger space, but internally, with space itself stretching. The very fabric of the cosmos is growing, meaning there's no edge to find because the space in which an edge might exist also expands. Adding to the enigma is the concept of the observable universe. This term defines the cosmic horizon, the furthest distance light has traveled to reach us since the dawn of time. At its limits, this sphere extends roughly 46 billion light-years in every direction, far larger than the 13.8 billion-year age of the universe might suggest. How can we see farther than the universe's age in years? This paradox arises because space itself stretches as light travels, dragging the distant galaxies we observe farther away, even as their light reaches us. Here's where it gets even stranger. The observable universe is not the full universe. Beyond our cosmic horizon lies an unobservable expanse, forever hidden because the light from those regions will never reach us. The universe expands faster than light can traverse it, creating a paradoxical situation where more universe exists than we can ever perceive. Does it go on forever, or does it wrap back on itself in a closed loop like the surface of a sphere? Scientists don't yet know, and perhaps we never will. What about the direction of time? Time, like space, is tied to the universe's expansion. The further back we look in time, the closer together everything was, until we approach the Big Bang itself. But the paradox lies in what happens next. What existed before the Big Bang? The idea of before might be meaningless because time and space were born together. The universe doesn't just defy boundaries in space. It also challenges the concept of a temporal beginning. Light, the ultimate traveler, plays a critical role in this cosmic mirage. While photons, or particles of light, race through space at the speed limit of the cosmos, they interact with the universe's stretching fabric. As they travel, their wavelengths elongate, a process called redshifting. Over immense distances, this redshifting moves light beyond the visible spectrum, rendering it undetectable. This means even the furthest observable light doesn't show the edge of the universe, but rather its past, a time when galaxies were younger and closer together. To complicate matters further, the expansion of the universe is accelerating. Dark energy, the mysterious force driving this acceleration, ensures that more and more of the universe slips beyond our observational reach. Imagine running toward a finish line that moves faster than you can sprint. No matter how much ground you cover, the boundary always escapes you. The universe's edge, if it exists, is not only unreachable, but perpetually retreating. Now, let's revisit the idea of infinity. Can the universe truly have no end? Infinity is not just a mathematical abstraction. It's a concept that strains the human mind. If the universe is infinite, then the observable cosmos is but a speck in an endless expanse. But if it's finite, how does it end? And if it does, what lies beyond that boundary? Theories range from the bizarre, our universe is a bubble in a multiverse foam, to the deeply philosophical, questioning whether the universe's edge is a feature our minds are even equipped to understand. This paradox doesn't just challenge scientists, it invites everyone to ponder the profound. If the universe has no edge, what does that say about our place in it? Are we central, a random point adrift in an endless sea, or something else entirely? And if there is an edge we cannot see, What mysteries lie beyond? Questions like these don't just push the boundaries of physics, they stretch the limits of imagination. As you look up at the night sky, remember that every star, every galaxy, is part of a cosmic story billions of years in the making. The edge of the universe may remain forever hidden, but the journey to understand it reveals the deeper truth. The cosmos is a place of endless wonder, where every answer births new questions. What lies beyond the horizon? The answer might be as infinite as the universe itself. Why can't we see the edge of the universe? Imagine standing on a mountaintop with a telescope so powerful it could peer across the entire cosmos. You point it outward, eagerly scanning for the universe's edge. But no matter how far you look, no boundary reveals itself. Why? Is the universe infinite? Or is there something fundamentally strange about the nature of space-time itself? This question opens one of the greatest paradoxes in astronomy, the elusive edge of the universe. At first glance, the problem seems simple. If the universe had a beginning, shouldn't it have an outer limit? The Big Bang, the widely accepted theory for how the universe began, describes a single moment 13.8 billion years ago when everything, space, time, matter, exploded into existence. So, shouldn't that explosion have a frontier, a leading edge racing outward like a cosmic shockwave? Paradoxically, the answer lies in how the universe expands, not outward like a balloon inflating into a larger space, but internally, with space itself stretching. The very fabric of the cosmos is growing, meaning there's no edge to find because the space in which an edge might exist also expands. Adding to the enigma is the concept of the observable universe. This term defines the cosmic horizon, the furthest distance light has traveled to reach us since the dawn of time. At its limits, this sphere extends roughly 46 billion light-years in every direction, far larger than the 13.8 billion year age of the universe might suggest. How can we see farther than the universe's age in years? This paradox arises because space itself stretches as light travels, dragging the distant galaxies we observe farther away even as their light reaches us. Here's where it gets even stranger. The observable universe is not the full universe. Beyond our cosmic horizon lies an unobservable expanse, forever hidden because the light from those regions will never reach us. The universe expands faster than light can traverse it, creating a paradoxical situation where more universe exists than we can ever perceive. Does it go on forever, or does it wrap back on itself in a closed loop like the surface of a sphere? Scientists don't yet know, and perhaps we never will. What about the direction of time? Time, like space, is tied to the universe's expansion. The further back we look in time, the closer together everything was, until we approach the Big Bang itself. But the paradox lies in what happens next. What existed before the Big Bang? The idea of before might be meaningless because time and space were born together. The universe doesn't just defy boundaries in space. It also challenges the concept of a temporal beginning. Light, the ultimate traveler, plays a critical role in this cosmic mirage. While photons, or particles of light, race through space at the speed limit of the cosmos, they interact with the universe's stretching fabric. As they travel, their wavelengths elongate, a process called redshifting. Over immense distances, this redshifting moves light beyond the visible spectrum, rendering it undetectable. This means even the furthest observable light doesn't show the edge of the universe but rather its past, a time when galaxies were younger and closer together. To complicate matters further, the expansion of the universe is accelerating. Dark energy, the mysterious force driving this acceleration, ensures that more and more of the universe slips beyond our observational reach. Imagine running toward a finish line that moves faster than you can sprint. No matter how much ground you cover, the boundary always escapes you. The universe's edge, if it exists, is not only unreachable, but perpetually retreating. Now, let's revisit the idea of infinity. Can the universe truly have no end? Infinity is not just a mathematical abstraction. It's a concept that strains the human mind. If the universe is infinite, then the observable cosmos is but a speck in an endless expanse. But if it's finite, how does it end? And if it does, what lies beyond that boundary? Theories range from the bizarre, our universe as a bubble in a multiverse foam, to the deeply philosophical, questioning whether the universe's edge is a feature our minds are even equipped to understand. This paradox doesn't just challenge scientists. It invites everyone to ponder the profound. If the universe has no edge, what does that say about our place in it? Are we central, a random point adrift in an endless sea, or something else entirely? And if there is an edge we cannot see, what mysteries lie beyond? Questions like these don't just push the boundaries of physics. They stretch the limits of imagination. As you look up at the night sky, remember that every star, every galaxy is part of a cosmic story billions of years in the making. The edge of the universe may remain forever hidden, but the journey to understand it reveals the deeper truth. The cosmos is a place of endless wonder, where every answer births new questions. What lies beyond the horizon? The answer might be as infinite as the universe itself. Why isn't the night sky fully lit? Take a moment to look up at the night sky. The darkness between the stars feels infinite, a deep void punctuated by brilliant points of light. But have you ever wondered why the night sky isn't ablaze with the glow of countless stars? After all, if the universe is filled with an infinite number of stars, shouldn't every direction we look be lit by their radiance? This seemingly simple question has puzzled astronomers and philosophers for centuries, giving rise to one of the most intriguing mysteries of the cosmos: Olbers' paradox. At first glance, the logic appears straightforward. Imagine the universe as a vast, unending expanse filled uniformly with stars. No matter where you look, your line of sight should eventually hit the surface of a star, just as standing in a dense forest ensures you always see a tree. In such a scenario, the night sky would be as bright as the surface of the sun, with no room for darkness to exist. Yet, that's not what we see. Instead, the sky is predominantly black, with stars scattered sparsely across its expanse. Why? To understand this paradox, let's journey back to the early 19th century, when the German astronomer Heinrich Wilhelm Olbers formally posed the problem. At the time, the prevailing view was that the universe was infinite, eternal, and static, a cosmos that had always existed and would always remain the same. Under these assumptions, the paradox seemed insurmountable. If the universe were truly infinite, with stars distributed evenly throughout, their combined light should saturate the sky. The night's darkness defied explanation. The first clue to solving this mystery came from an unexpected source: the nature of light itself. Light travels at a finite speed, 300,000 kilometers per second. This means that when we gaze at distant stars or galaxies, we're not seeing them as they are now, but as they were when their light began its journey toward us. For nearby stars, this delay is negligible, measured in years or centuries. But for the most distant objects, the light we observe could have been traveling for billions of years. This limitation, combined with the finite age of the universe, provides a crucial insight into Olbers' paradox. Our universe is approximately 13.8 billion years old, a staggering number, but still finite. This means that the light from stars and galaxies beyond a certain distance, more than 13.8 billion light-years away, hasn't had enough time to reach us. The darkness of the night sky is, in part, a consequence of this cosmic time limit. We're surrounded by an observable universe, a sphere defined not by physical boundaries, but by the reach of light itself. Beyond this horizon lies a vast, unobservable expanse, eternally hidden from view. But this alone doesn't fully resolve the paradox. After all, even within the observable universe, there are billions of galaxies, each containing billions of stars. Shouldn't their collective light still flood the sky? This is where the second piece of the puzzle comes into play: the expansion of the universe. Since the Big Bang, space itself has been stretching, carrying galaxies away from each other like dots on the surface of an inflating balloon. As this expansion occurs, the wavelengths of light traveling through space are stretched as well, a phenomenon known as redshift. Redshift has profound implications for how we perceive the cosmos. Light from distant galaxies is shifted out of the visible spectrum, becoming infrared or even microwave radiation, forms of energy our eyes cannot detect. This stretching effectively dims the light from distant objects, ensuring that even the combined glow of billions of galaxies doesn't overwhelm the night sky. What we see instead is a faint, diffuse background glow, detectable only with specialized instruments. This glow is known as the cosmic microwave background, CMB, a relic of the universe's earliest moments. Another factor contributing to the darkness is the life cycle of stars. Stars are not eternal. They are born, burn brightly for millions or billions of years, and then fade or die. The universe is filled with regions of gas and dust where stars are forming, as well as remnants of long-extinguished stars. The light from these regions is often obscured by the very material that gives birth to new stars, adding another layer of complexity to the cosmic glow. Olbers' paradox also invites us to reconsider the nature of infinity. If the universe were truly infinite, containing an infinite number of stars, the paradox would hold. But modern cosmology suggests that while the universe may be spatially infinite, its observable portion is limited by time, distance, and the laws of physics. This duality, an infinite universe with a finite observable limit, offers a compelling resolution to the paradox, blending mathematical theory with empirical observation. As we ponder the paradox, it's worth reflecting on its philosophical implications. The darkness of the night sky isn't just an absence of light. It's a window into the history and structure of the cosmos. Every patch of darkness represents regions where light has yet to reach us, where the universe is still expanding beyond our comprehension. It's a reminder of the immense scale of the cosmos and the limits of our perception. Olbers' paradox also underscores the importance of asking seemingly simple questions. What began as an observation about the night sky led to profound insights into the age, structure, and dynamics of the universe. It challenges us to look beyond the surface of everyday phenomena and explore the deeper truths hidden within. So, the next time you find yourself under a starry sky, take a moment to appreciate the profound mystery of its darkness. In every shadow lies a story of cosmic expansion, ancient starlight, and the limits of human understanding. Why isn't the night sky fully lit? Because the universe, in all its vastness, holds secrets that even light cannot fully reveal. Where's everybody? Picture this. In a universe teeming with billions of galaxies, each containing billions of stars, many of which likely host planets, some of which are potentially habitable, why is the cosmos so eerily silent? This haunting question, known as the Fermi paradox, poses one of the greatest enigmas of modern astronomy. If life is as abundant as the vastness of the universe suggests, then where is everybody? Why haven't we heard the whisper of alien civilizations reaching out across the void? To truly grasp the weight of this paradox, we must consider the sheer scale of the cosmos. Our Milky Way galaxy alone contains an estimated 100 billion stars, many of which are orbited by planets. Advances in astronomy reveal that a significant fraction of these exoplanets lie within the habitable zone, a region where conditions might allow liquid water to exist, a critical ingredient for life as we know it. Expanding outward, the observable universe holds over 2 trillion galaxies. The statistical probability of life existing elsewhere is staggeringly high. Enter Enrico Fermi, the brilliant physicist who, during a casual lunchtime conversation in 1950, famously asked, "Where is everybody?" His question cut through the optimism of the post-war scientific era, confronting humanity with the uncomfortable possibility that intelligent extraterrestrial life might be far more elusive or rarer than we imagine. Since then, countless theories have emerged to explain the silence of the stars, ranging from the scientific to the philosophical, each one peeling back a layer of the paradox. One of the most compelling explanations is the Great Filter hypothesis. This theory suggests that somewhere along the pathway from simple life to advanced civilizations capable of interstellar communication, there's a bottleneck, a stage so difficult to overcome that few, if any, civilizations succeed. The filter could occur early in the process, such as the leap from single-celled organisms to complex life, or it could come later, perhaps when civilizations reach a point of technological maturity that leads to their self-destruction. This raises a chilling question. Is humanity's development of nuclear weapons, artificial intelligence, or climate-altering technologies evidence that we're nearing our own filter? Another possible solution lies in the zoo hypothesis. What if extraterrestrial civilizations are aware of us, but choose not to interfere, much like zookeepers observing animals in a preserve? This idea suggests that advanced beings might have ethical or strategic reasons for avoiding contact, perhaps believing that humanity must first reach a certain level of development before joining a galactic community. While speculative, this theory aligns with the eerie lack of observable evidence despite decades of searching. Could it be that we're simply looking in the wrong way? Traditional searches for extraterrestrial intelligence rely on detecting radio signals or other forms of electromagnetic communication. But what if advanced civilizations have moved beyond such primitive technologies? Just as humanity has transitioned from wired telegraphs to quantum computing, alien civilizations might employ methods of communication or travel that we cannot yet comprehend. This idea, known as the technology gap hypothesis, suggests that we might be like ants trying to interpret the workings of a satellite. Then there's the rare Earth hypothesis, which posits that the conditions allowing for life are far more unique than we assume. While planets in the habitable zone might be common, factors like stable climate, protective magnetic fields, and the presence of a large moon to stabilize planetary tilt may be rare. Under this theory, Earth's ability to support complex life might be an extraordinary cosmic fluke. The silence might also be a matter of timing. Civilizations could rise and fall like waves on a cosmic ocean, with their lifespan so brief on astronomical timescales that overlap is rare. Imagine a civilization a million light years away that flourished for 10,000 years. A blink of an eye in cosmic history. By the time their signals reach us, they could already be extinct or vice versa. This concept, known as temporal misalignment, highlights the fragility of intelligent life in an ever-changing universe. But what if the Fermi paradox isn't a paradox at all? Some scientists argue that humanity has only just begun its search, akin to dipping a cup into the ocean and finding no fish. The cosmos is vast beyond imagination, and our tools for exploring it remain rudimentary. The ongoing search for biosignatures, technosignatures, and exoplanets is still in its infancy, and the silence might simply reflect the limits of our technology and understanding. As unsettling as these theories may be, they also highlight the resilience of human curiosity. The Fermi paradox isn't just a question about alien life. It's a reflection of our desire to understand our place in the universe. It forces us to confront existential questions about our uniqueness, our future, and our responsibilities as stewards of Earth. One possible resolution lies not in waiting for contact, but in becoming the explorers ourselves. As humanity develops technologies for interstellar travel, from solar sails to generation ships, the prospect of expanding beyond our home planet grows closer to reality. If intelligent life exists elsewhere, perhaps it's waiting for us to take the first step. Ultimately, the Fermi paradox challenges us to think bigger, to push the boundaries of science, and to embrace the unknown. The silence of the cosmos is not an answer, but an invitation, a call to explore, to question, and to wonder. Where's everybody? The answer might not lie in distant stars, but in the future of our own journey into the depths of space. Could the universe create itself? Imagine finding an ancient book filled with intricate diagrams and equations that unlock the secrets of the universe. You meticulously study it, mastering its wisdom, and eventually use its knowledge to create the very same book, ensuring it survives for future generations. But here's the twist. Where did the book originally come from? This mind-bending loop is the essence of the bootstrap paradox, a concept that challenges our understanding of causality, time, and even the origin of the universe itself. The bootstrap paradox is a thought experiment rooted in the idea of self-creation, an object, idea, or event existing without a clear point of origin, essentially pulling itself into existence. While often associated with science fiction and time travel, this paradox raises profound questions about the universe's existence. Could the cosmos, much like the hypothetical book, be a self-sustaining loop with no discernible beginning or end? To understand the paradox, we must first examine the nature of causality. In everyday experience, cause precedes effect. If you throw a rock into a pond, the ripples that form are the result of your action. But the bootstrap paradox disrupts this sequence, creating a situation where cause and effect are indistinguishable. If the book exists only because you created it from its future version, then where does the original information reside? Similarly, if the universe created itself, what initiated the process? This paradox is not purely speculative. It's deeply connected to the nature of time and space-time. According to Einstein's theory of general relativity, time is not linear, but part of a four-dimensional fabric that can bend, twist, and fold. Under certain extreme conditions, such as those near black holes or hypothetical wormholes, time loops, known as closed time-like curves, could theoretically exist. These loops create the possibility of events influencing their own causes, setting the stage for scenarios like the bootstrap paradox. But how does this relate to the universe's origin? The leading cosmological theory, the Big Bang, posits that the universe began as a singularity, a point of infinite density and energy, about 13.8 billion years ago. Yet, the theory doesn't explain what caused the singularity or what existed before it. In fact, the concept of before may not even apply, as time itself is thought to have emerged with the Big Bang. This raises a tantalizing question. Could the universe be its own cause, existing in a self-contained loop where the end gives rise to the beginning? One theory that explores this idea is the concept of a cyclic universe. Unlike the traditional Big Bang model, which envisions a single creation event followed by endless expansion, the cyclic model suggests that the universe undergoes infinite cycles of birth, death, and rebirth. In this framework, the end of one universe triggers the creation of the next, forming an eternal loop. While speculative, this idea aligns with certain interpretations of string theory, which propose that our universe's Big Bang could be the result of a collision between higher-dimensional branes. The bootstrap paradox also finds echoes in quantum mechanics, where the boundaries between cause and effect blur. In the quantum realm, particles can appear to exist in multiple states simultaneously, and their behavior can influence each other instantaneously, even across vast distances, a phenomenon known as quantum entanglement. Some interpretations of quantum mechanics, such as the retrocausal interpretation, suggest that events in the future could influence the past, opening the door to self-creating systems. Critics of the bootstrap paradox argue that it violates fundamental laws of physics, particularly the principle of conservation of energy. If the universe created itself, where did the energy come from? One possible answer lies in the nature of space-time itself. Quantum field theory suggests that empty space is not truly empty, but filled with fluctuating energy, a concept known as the quantum vacuum. Could the universe have arisen from these quantum fluctuations, effectively creating something from nothing? This idea, while still controversial, offers a potential resolution to the paradox. Philosophically, the bootstrap paradox challenges our deepest assumptions about existence. Human intuition is rooted in linear thinking. Every event has a cause, every story a beginning and an end. Yet the paradox suggests a reality where these distinctions break down, where existence is not a sequence, but a self-sustaining loop. This raises profound questions about meaning and purpose. If the universe has no external cause, does that diminish its significance? Or does it make its existence even more extraordinary? The paradox also forces us to confront the limits of human understanding. The universe operates on scales of time, space, and complexity that far exceed our everyday experience. Concepts like causality and time, so fundamental to our perception of reality, may be inadequate for describing the true nature of the cosmos. Could the bootstrap paradox be a clue that our understanding of physics is incomplete, pointing toward deeper, more unified theories of existence? As speculative as these ideas are, they serve an essential purpose: expanding the boundaries of human thought. The bootstrap paradox isn't just a puzzle for physicists and philosophers. It's a reminder of the universe's capacity to astonish and confound. By grappling with such paradoxes, we're not only exploring the mysteries of the cosmos, but also redefining what it means to seek knowledge. So, could the universe create itself? The answer may forever elude us, hidden in the folds of space-time or the equations of quantum mechanics. But the journey to understand this paradox brings us closer to the ultimate truth. that the universe, in all its complexity, is a place where questions often outnumber answers, and the act of asking them is what makes us truly human. The black hole information paradox. Does information disappear forever? A star collapsing under its own gravity, forming a black hole so dense that not even light can escape its pull. These cosmic monsters are the ultimate destroyers, devouring everything that ventures too close. But here's the question that has haunted physicists for decades. What happens to the information about the things that fall into a black hole? Is it lost forever, erased from existence? This question leads us into one of the most profound and unresolved mysteries in modern physics, the black hole information paradox. At its core, this paradox arises from a conflict between two foundational pillars of science: quantum mechanics and general relativity. Quantum mechanics, which governs the behavior of particles on the smallest scales, asserts that information, the fundamental description of a system state, cannot be destroyed. This principle is called unitarity and is a cornerstone of the theory. On the other hand, general relativity, Einstein's theory of gravity, predicts that anything falling into a black hole is crushed to an infinitely dense point called the singularity, seemingly obliterating all traces of its original form. This apparent contradiction becomes most troubling when we consider the ultimate fate of a black hole itself. According to Stephen Hawking's groundbreaking work in the 1970s, black holes are not completely black. They emit radiation, now known as Hawking radiation, due to quantum effects near their event horizons, the boundaries beyond which nothing can escape. Over immense timescales, this radiation causes black holes to slowly lose mass and eventually evaporate entirely. But here's the problem. If a black hole disappears, what happens to the information about the things it consumed? Is it encoded in the radiation, or is it lost forever? If the information is truly lost, it violates unitarity and throws quantum mechanics into chaos. Such a violation would undermine the predictability of physical laws, suggesting that the universe could operate on fundamentally unknowable principles. To physicists, this is an unacceptable conclusion. The idea that black holes could destroy information challenges the very foundation of how we understand reality. The black hole information paradox has inspired some of the most brilliant minds in science to propose solutions, each one pushing the boundaries of physics. One of the earliest ideas was that information might be stored in some form within the black hole itself, perhaps at the singularity. However, this explanation is unsatisfactory because the singularity lies beyond the event horizon, hidden from the rest of the universe. Information trapped there would be effectively inaccessible, rendering it as good as lost. A more recent and widely discussed solution comes from the idea of holography. This theory suggests that all the information about objects falling into a black hole might be encoded on its event horizon, the two-dimensional boundaries surrounding the black hole. In this framework, the black hole behaves like a cosmic hologram, with its surface storing information about its interior in much the same way that a holographic image contains three-dimensional data on a two-dimensional surface. This idea is rooted in the holographic principle, a concept emerging from string theory, which posits that the entire universe might itself be a hologram. But how could the information escape during evaporation? Here's where things get even stranger. Some theorists propose that Hawking radiation is not random, but carries subtle imprints of the information from the black hole's interior. While these imprints would be incredibly faint and difficult to detect, they could, in principle, preserve the lost information. This idea aligns with the concept of quantum entanglement, where particles remain connected in such a way that the state of one instantaneously affects the state of the other, regardless of distance. If the particles comprising Hawking radiation are entangled with those inside the black hole, they might serve as a bridge for information. Another fascinating proposal is the firewall hypothesis, which suggests that the event horizon itself might not be as benign as once thought. Instead, it could be a searing barrier of high-energy particles that obliterates anything attempting to cross it. This scenario preserves unitarity by ensuring that information is not lost but released in a highly transformed state. However, the idea of firewalls introduces its own problems, as it clashes with another cherished principle of physics, the equivalence principle, which states that an observer falling into a black hole should not experience anything unusual at the event horizon. The debate over the black hole information paradox has also led to a radical rethinking of space and time. Some researchers suggest that black holes might not truly destroy information, but instead act as portals to other regions of space-time. In this view, the information might escape through a process akin to a wormhole, emerging in another part of the universe, or even another universe entirely. While highly speculative, this idea aligns with theories that attempt to unify quantum mechanics and general relativity, offering a glimpse into the deeper structure of reality. Despite decades of research, the black hole information paradox remains unresolved. It represents more than just a technical puzzle. It's a doorway to the unknown, a challenge that could lead to revolutionary breakthroughs in our understanding of the universe. By grappling with this paradox, scientists hope to uncover a theory of quantum gravity, a framework that reconciles the principles of quantum mechanics with the curvature of space-time described by general relativity. Philosophically, the paradox forces us to confront the nature of information itself. If information is never truly lost, what does that mean for the universe as a whole? Does every particle, every interaction, every moment leave an indelible mark on the fabric of reality? And if black holes can preserve information, even as they evaporate, does this imply that the cosmos has a built-in mechanism for memory, a kind of cosmic ledger that ensures nothing is ever truly forgotten? The black hole information paradox reminds us that the universe is not only stranger than we imagine, but stranger than we can imagine. It challenges us to rethink our assumptions about time, space, and the very fabric of existence. Does information disappear forever? The answer lies somewhere in the interplay of the cosmos's deepest mysteries, waiting for the next leap in human understanding. The quantum measurement paradox. Is reality truly real? Imagine standing in a room with a cat sealed inside a box. You can't see or hear the cat, but there's a device in the box that could release a poison depending on a random quantum event. Until you open the box, you're left with a haunting thought. Is the cat alive, dead, or somehow both at the same time? This thought experiment, famously known as Schrödinger's cat, is not just a quirky metaphor. It embodies one of the most profound mysteries in physics, the quantum measurement paradox. At the heart of this paradox lies the peculiar nature of quantum mechanics. Unlike the predictable, clockwork universe described by classical physics, the quantum world is governed by probabilities. Particles such as electrons and photons don't have definite properties until they're measured. Instead, they exist in a superposition of all possible states, described mathematically by a wave function. When a measurement is made, this wave function collapses, forcing the particle into one specific state. But here's the paradox. What determines when and how this collapse occurs? And what role does the act of observation play? Let's start with the double-slit experiment, one of the most famous demonstrations of quantum behavior. In this experiment, particles like electrons are fired at a barrier with two slits. When unobserved, the particles create an interference pattern on the screen behind the slits, as if they behave like waves, passing through both slits simultaneously. However, when a detector is placed to observe which slit each particle goes through, the interference pattern disappears. The particles behave like particles, choosing one slit or the other. It's as if the act of measurement determines the particle's reality, forcing it to decide its state. This phenomenon raises profound questions about the nature of reality. Does the particle exist in all possible states until it's observed? If so, what qualifies as an observer? Is it the measuring device, a conscious mind, or something else entirely? These questions strike at the core of the quantum measurement problem, a puzzle that has defied resolution for nearly a century. One of the earliest attempts to interpret this paradox was the Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg. This interpretation suggests that the wave function represents a probability distribution, not a physical reality, and collapses only when a measurement is made. However, the Copenhagen interpretation leaves open the question of what constitutes a measurement and why it causes collapse. Enter the many-worlds interpretation, a radical alternative proposed by physicist Hugh Everett. According to this view, the wave function never collapses. Instead, every possible outcome of a quantum event actually occurs, but in separate, parallel universes. In the case of Schrödinger's cat, the universe splits into two, one where the cat is alive and one where it's dead. These universes coexist, but we perceive only one because our consciousness follows a single branch. While this interpretation avoids the problem of wave function collapse, it introduces a new question. If every possibility occurs, what determines which branch we experience? Another approach, known as objective collapse theories, suggests that wave function collapse is a physical process that occurs spontaneously under certain conditions, independent of observation. These theories propose that superpositions become unstable when involving macroscopic systems, leading to collapse. However, objective collapse remains unproven, and its mechanisms are still under intense scrutiny. Quantum mechanics also introduces the concept of entanglement, a phenomenon Einstein famously derided as spooky action at a distance. When two particles become entangled, their properties are linked, such that measuring one instantly determines the state of the other, regardless of the distance between them. This seemingly violates the speed limit of the universe. Nothing can travel faster than the speed of light, raising questions about how information is transmitted in the quantum realm. The paradox deepens when we consider the role of consciousness. Some interpretations, like the von Neumann-Wigner hypothesis, propose that consciousness itself causes wave function collapse. In this view, reality doesn't solidify until a conscious observer interacts with it. While this idea fascinates philosophers and mystics, it remains controversial among physicists, as it raises the uncomfortable possibility that human awareness plays a fundamental role in shaping the universe. Could the answer lie in the nature of reality itself? Some physicists suggest that the quantum world might not be real in the traditional sense. Instead, reality could be an emergent phenomenon, arising from the interactions of particles and fields. In this framework, the collapse of the wave function might be a reflection of our limited ability to perceive the underlying quantum substrate, rather than a fundamental event. The quantum measurement paradox has profound implications for our understanding of the universe. If reality depends on observation, what does that mean for the cosmos before the emergence of conscious beings? Did the universe exist in a superposition until life evolved to observe it? Or is consciousness itself a quantum phenomenon, intricately linked to the fabric of reality? This paradox also challenges our assumptions about determinism. In the classical world, every cause has an effect, and the future is determined by the present. But in the quantum realm, randomness rules. Particles behave unpredictably, and events occur with probabilities, not certainties. This randomness introduces a level of unpredictability into the universe, suggesting that reality is not as deterministic as we once believed. The quantum measurement paradox is more than a scientific conundrum. It's a philosophical riddle that forces us to confront the nature of existence. Are we passive observers of an objective reality, or active participants in its creation? Does the universe exist independently of us, or is it inextricably tied to our awareness? While the answers remain elusive, one thing is certain. The quantum world defies intuition, challenging us to expand our understanding of what's possible. Is reality truly real? The answer may lie not in the equations of physics, but in the very act of questioning itself. A reminder that the search for truth is as infinite and mysterious as the universe it seeks to explain. The heat-death paradox. Can the universe truly die? Picture the universe billions, perhaps trillions of years into the future. The stars have burned out, galaxies have disintegrated, and the cosmos has become a vast, dark void where nothing stirs. This is the chilling vision of the heat-death of the universe, a theoretical endpoint where all energy is evenly distributed, leaving no room for life, motion, or change. But is this the inevitable fate of the cosmos? Or is there a paradox hidden within this stark prediction? Can the universe truly die? Or could new cycles of creation emerge from its ashes? To understand the concept of heat death, we must delve into the second law of thermodynamics, one of the most fundamental principles of physics. This law states that in any closed system, entropy, a measure of disorder or randomness, tends to increase over time. In simpler terms, energy naturally flows from concentrated states, like a star, to more diffuse states like the empty space around it. Over cosmic timescales, This process leads to the gradual running down of the universe, as energy becomes so evenly distributed that no useful work can be performed. This slow drift toward equilibrium creates a paradoxical tension. On the one hand, the laws of physics dictate that energy cannot be destroyed. It's conserved, merely changing forms. On the other hand, the universe's increasing entropy suggests an irreversible decline into stagnation. If energy persists but becomes unusable, does the universe truly die? Or does it transition into a new, unrecognizable state? The concept of heat death dates back to the 19th century, when physicists like Lord Kelvin and Rudolf Clausius recognized the implications of thermodynamic principles on a universal scale. They envisioned a future where all stars had exhausted their nuclear fuel, black holes had evaporated, and the cosmos had settled into a cold, featureless expanse. This scenario aligns with the Big Freeze, one of the leading theories for the universe's end, driven by its ongoing expansion. But here's where the paradox emerges. While heat death implies the end of all activity, it also suggests a kind of timeless permanence. In a state of maximum entropy, where all processes cease, the very concept of time loses meaning. Without change, time itself becomes indistinguishable from eternity. Does this mean the universe exists forever in a frozen state? Or does the cessation of time signify the end of existence altogether? Modern cosmology adds further complexity to this grim picture. Observations reveal that the universe's expansion is accelerating, driven by a mysterious force called dark energy. If this acceleration continues indefinitely, it could lead to a future where galaxies move so far apart that they vanish beyond each other's observable horizons. This isolation would deepen the cosmic silence, leaving individual galaxies to drift into entropy alone. Some theories even propose a big rip, where dark energy becomes so dominant that it tears apart galaxies, stars, and eventually atoms, reducing the universe to a bizarre singularity. Yet, the idea of universal death isn't universally accepted. Some theories challenge the finality of heat death, suggesting that the cosmos might undergo cycles of rebirth. In cyclic cosmology, the universe doesn't end but transitions through a series of expansions and contractions, much like a cosmic heartbeat. After reaching maximum entropy, the universe might collapse in a big crunch, followed by another big bang. This endless cycle of creation and destruction offers an alternative to the static, lifeless future envisioned by heat death. Quantum mechanics also provides a potential loophole in the heat death narrative. On the quantum scale, even the emptiest vacuum is not truly empty, but filled with fluctuations, temporary appearances of particles and energy. Could these fluctuations spark new universes, even in a state of maximum entropy? The concept of a multiverse suggests that our universe might be just one bubble in a vast cosmic foam, with new universes constantly forming in regions of high energy density. If true, the death of one universe could give rise to countless others, each with its own laws and constants. Philosophically, the heat death paradox raises profound questions about the nature of existence and the meaning of life in a seemingly finite cosmos. If the universe is destined to decay into nothingness, what does that imply about our place within it? Does our brief moment of awareness in the cosmic timeline carry less significance? Or does it become even more precious in the face of eternity? This paradox also invites us to reconsider the concept of death itself. In biology, death is not the end of matter, but a transformation, as organic components break down and return to the environment, fueling new life. Could the universe follow a similar path, where heat death is not an end, but a transition, its energy repurposed in ways we cannot yet comprehend? The heat death paradox also pushes the boundaries of human imagination. What would it mean to exist in a universe approaching maximum entropy? Could advanced civilizations find ways to survive, perhaps by manipulating quantum fluctuations or tapping into exotic energy sources? Or would intelligence itself fade into irrelevance as the cosmos settles into stillness? These speculative questions highlight the resilience of human curiosity, even in the face of existential uncertainty. While the idea of heat death paints a bleak picture, it also underscores the incredible dynamism of the cosmos. The universe began as an unimaginably hot, dense point, bursting into existence with the Big Bang. From this singularity emerged galaxies, stars, planets, and the conditions for life. The same laws that predict the universe's eventual decline also govern its astonishing creativity, enabling complexity and consciousness to arise from chaos. So, can the universe truly die? The answer depends on how we define death. If death means an end to activity and change, then heat death might fit the description. But if death implies a cessation of existence, the paradox leaves room for hope. Hope that even in the darkest reaches of entropy, the universe retains the potential for renewal, transformation, and new beginnings. The dark matter and dark energy paradox. Is 95% of the universe missing? Imagine gazing into the vast expanse of space, marveling at galaxies, stars, and planets scattered across the cosmos. Everything you see, the light from distant stars, the gas clouds swirling between galaxies, and even the planets under telescopes, makes up only about 5% of the universe. The other 95%? It's invisible, enigmatic, and utterly mysterious. This astonishing revelation has given rise to one of the most perplexing paradoxes in modern astronomy. If most of the universe is composed of dark matter and dark energy, why can't we find it, see it, or fully understand it? To comprehend this mystery, we must first explore what scientists mean by dark matter and dark energy. These terms describe two distinct phenomena, both crucial to understanding the structure and fate of the universe. Dark matter, which accounts for about 27% of the universe, is an invisible form of matter that doesn't emit, absorb, or reflect light. Dark energy, on the other hand, makes up about 68% of the universe and is believed to be the driving force behind the cosmos's accelerating expansion. Together, they dominate the universe's mass-energy composition, yet their true nature remains elusive. The story of dark matter begins with an observation that defied expectations. In the 1930s, astronomer Fritz Zwicky studied galaxy clusters and noticed something peculiar. The galaxies within these clusters were moving far faster than their visible mass could account for, based on gravitational calculations. If gravity were acting only on the matter we could see, stars, gas, and dust, these clusters should have flown apart. Zwicky proposed the existence of unseen dark matter to explain the additional gravity holding these galaxies together. Decades later, astronomer Vera Rubin confirmed this phenomenon on smaller scales, observing the rotational speeds of individual galaxies. She discovered that the outer regions of galaxies rotated just as fast as their inner regions, defying the expectations set by Newtonian physics. If visible matter were the only contributor to gravity, the outer edges should rotate more slowly. These observations provided compelling evidence for dark matter, a substance that interacts gravitationally but remains invisible to electromagnetic detection. Yet, dark matter's true nature remains one of the greatest unsolved mysteries in physics. What is it made of? The leading candidates are hypothetical particles like WIMPs, weakly interacting massive particles, and axions, but neither has been detected despite extensive searches using underground detectors, particle accelerators, and even cosmic ray studies. Another possibility is that dark matter could consist of primordial black holes, remnants from the universe's earliest moments. However, these ideas remain speculative, leaving scientists with more questions than answers. While dark matter explains the gravitational glue holding galaxies together, dark energy addresses an entirely different cosmic puzzle. In the late 1990s, two teams of astronomers studying distant supernovae discovered that the universe's expansion wasn't slowing down as expected. It was speeding up. This startling discovery suggested the presence of a mysterious force counteracting gravity on a cosmic scale. That force was named dark energy. But what exactly is dark energy? One hypothesis is that it's an inherent property of space itself, known as the cosmological constant. Einstein first introduced this concept in his equations of general relativity, but later dismissed it as his greatest blunder after the discovery of the expanding universe. However, the accelerating expansion revived the cosmological constant as a leading explanation for dark energy. Another possibility is that dark energy arises from a dynamic field permeating the universe, similar to how the Higgs field gives particles mass. This quintessence field could vary over time and space, adding complexity to the nature of cosmic acceleration. Yet another theory suggests that our understanding of gravity might be incomplete. Modified gravity models propose that the observed effects of dark energy could arise from deviations in how gravity behaves on large scales. The paradox of dark matter and dark energy becomes even more perplexing when we consider how little we understand about the observable universe's structure. Dark matter forms the scaffolding upon which galaxies are built. Simulations of cosmic evolution show that without dark matter's gravitational influence, the large-scale structure of the universe, its web of interconnected galaxies and clusters, couldn't have formed. Yet, we've never directly observed a dark matter particle. Meanwhile, dark energy determines the universe's ultimate fate. If its influence grows stronger over time, the cosmos could experience a big rip where galaxies, stars, and even atoms are torn apart. Alternatively, dark energy might weaken, allowing gravity to regain dominance and causing the universe to collapse in a big crunch. A third possibility is that the universe will continue expanding forever, gradually approaching a state of heat death. The interplay between dark matter and dark energy also raises philosophical questions about the nature of existence. If 95% of the universe is invisible and largely incomprehensible, what does that say about our ability to understand the cosmos? Are we limited by our senses, our instruments, or perhaps the very structure of reality itself? The search for dark matter and dark energy represents not just a quest for scientific answers, but a profound exploration of what it means to seek knowledge in a universe that conceals so much. Efforts to unravel these mysteries are ongoing. The Large Hadron Collider, space telescopes like the James Webb Space Telescope, and ground-based observatories like the Vera C. Rubin Observatory are all poised to provide new insights. At the same time, advancements in theoretical physics, such as string theory and quantum gravity, may offer deeper frameworks for understanding the cosmos's unseen components. As we probe the dark heart of the universe, one thing becomes clear. The existence of dark matter and dark energy fundamentally changes our perception of reality. They remind us that what we see is only a fraction of what exists, a thin veneer over a vast, hidden expanse. Is 95% of the universe missing, or is it simply waiting to be discovered? The answer lies in the frontier of human curiosity, where each new question brings us closer to illuminating the darkness. The multiverse paradox. How many universes could exist? Imagine standing on a beach, gazing at the countless grains of sand stretching to the horizon. Now imagine that each grain represents not just a star or a galaxy, but an entire universe. This is the breathtaking vision of the multiverse, a theoretical concept suggesting that our universe is just one of countless others. But if this idea holds true, it raises profound questions about existence, reality, and the very nature of science. How many universes could exist, and why can't we see them? The idea of a multiverse emerges from several branches of physics and cosmology, each offering its unique perspective on how these alternate realities might arise. One of the most well-known theories stems from cosmic inflation, a model describing the universe's rapid expansion immediately after the Big Bang. According to this theory, as the universe inflated, different regions may have stopped expanding at different times, forming bubbles of space-time. Each bubble would evolve into its own universe, potentially with entirely different physical laws, constants, and structures. Our universe would be just one bubble in this vast cosmic foam. But how vast is this foam? If inflation continues indefinitely in some regions, a concept called eternal inflation, the number of universes could be effectively infinite. This leads to the paradox of infinity, where anything that can happen not only does happen, but happens an infinite number of times. In this scenario, there could be countless versions of you reading this sentence right now, each in slightly different circumstances. Some universes might resemble ours closely, while others could be so radically different that the very idea of life might take on an entirely alien meaning. The multiverse concept also arises in quantum mechanics, particularly through the many worlds interpretation. In this view, every quantum event with multiple possible outcomes splits the universe into branches, each representing one of those outcomes. For instance, if you flip a coin, the multiverse splits into two, one where the coin lands heads and another where it lands tails. These branches coexist, but are isolated from each other, creating a seemingly endless web of alternate realities. While these theories are fascinating, they also challenge our understanding of science itself. A key principle of scientific inquiry is falsifiability, the ability to test and potentially disprove a hypothesis. If other universes are inaccessible to us, how can we confirm their existence? Critics argue that the multiverse, while mathematically plausible, veers into the realm of philosophy or metaphysics rather than empirical science. Yet, some scientists believe the multiverse might leave detectable imprints on our own universe. For example, if our bubble universe collided with another during inflation, it could have left scars in the cosmic microwave background, the faint glow of radiation left over from the Big Bang. Detecting such anomalies would provide indirect evidence of other universes, bridging the gap between theory and observation. The multiverse also raises profound philosophical and existential questions. If an infinite number of universes exist, does that diminish the significance of our own? Are we merely one of countless cosmic accidents, our lives no more meaningful than the countless alternate versions of ourselves? Or does the vastness of the multiverse elevate the importance of our existence? A reminder that even amidst infinite possibilities, we experience this unique moment in our reality. The possibility of a multiverse also challenges traditional notions of causality and purpose. If universes can arise spontaneously from quantum fluctuations or the dynamics of inflation, do we need a creator or a fundamental reason for their existence? Some proponents of the multiverse argue that it resolves the fine-tuning problem, the observation that the physical constants of our universe seem perfectly calibrated for life. In a multiverse, countless universes with varying constants would exist, and we simply happen to inhabit one where the conditions are right for life. This explanation, while elegant, shifts the question of origins to a higher level. Why does the multiverse itself exist? Interestingly, the multiverse concept finds parallels in ancient philosophy and mythology. Many cultures envisioned a cosmos filled with multiple realms or planes of existence, from the Norse Yggdrasil's 9 worlds to Hindu cosmology's cycles of creation and destruction. These stories, though symbolic, resonate with modern theories, suggesting that humanity's fascination with alternate realities spans both science and spirituality. But how do we reconcile the multiverse with our everyday experience? If infinite universes exist, why do we perceive only this one? Some physicists suggest that our consciousness is bound to the physical parameters of our universe, much like a fish confined to its pond. Other universes might exist beyond our perception, inaccessible through the dimensions we inhabit. Alternatively, the act of observation itself could be what isolates our universe, collapsing the wave of possibilities into a singular reality. Despite its speculative nature, the multiverse concept drives scientific innovation and exploration. String theory, one of the most ambitious frameworks in theoretical physics, suggests that different universes could arise from variations in how extra dimensions are compactified. These dimensions, curled up so tightly that they're imperceptible at human scales, might hold the key to understanding why our universe is structured the way it is. The multiverse also inspires creative thinking beyond physics. In literature, art, and film, alternate realities have become a fertile ground for storytelling, reflecting our collective yearning to explore the what-ifs of existence. From the parallel worlds of science fiction to the multiverse adventures of superhero films, these stories echo humanity's innate curiosity about the unknown. So, how many universes could exist? The answer, as far as we can tell, may be infinite. But the true significance of the multiverse lies not in its sheer number, but in the questions it compels us to ask. What defines reality? How does our universe fit into the broader cosmic tapestry? And what does it mean to exist in a realm where possibilities stretch beyond imagination? The multiverse paradox reminds us that the universe, or perhaps the multiverse, is not only stranger than we think, but stranger than we can think. In this boundless sea of realities, our universe is a single grain of sand, unique yet interconnected with the infinite possibilities around it. And as we continue to explore, we are left with the humbling realization that even the grandest questions may lead to even grander mysteries. The anthropic principle paradox. Is the universe fine-tuned for life? Imagine walking into a room and finding every object arranged perfectly to meet your needs. The lighting is just right, the air temperature is comfortable, and the chair is designed for your body. Now scale this analogy to the universe itself. The laws of physics, the constants of nature, and the very structure of space-time all seem perfectly calibrated to allow life to exist. But why is this the case? This question is at the heart of the anthropic principle paradox, which asks whether the universe is fine-tuned for life, or if we simply perceive it that way because we're here to ask the question. At first glance, the idea of a fine-tuned universe is astonishing. Consider the fundamental constants of nature, such as the gravitational constant or the strength of the electromagnetic force. If these values were even slightly different, the universe as we know it would be unrecognizable. Stars might never form, or atoms could fail to hold together, making life, and perhaps existence itself, impossible. This apparent precision has led some to argue that the universe must have been intentionally designed or guided toward life. However, this reasoning introduces a paradox. Are the constants of the universe truly fine-tuned? Or is this a result of our observational bias? After all, we exist in a universe that supports life, so it's no surprise that we find it compatible with our existence. This perspective forms the basis of the anthropic principle, which comes in two main forms: the weak anthropic principle, WAP, and the strong anthropic principle, SAP. The weak anthropic principle states that we observe the universe's properties the way they are, because only in such a universe could observers like us exist. In other words, the universe isn't fine-tuned for life. Instead, life emerged in a universe that happened to have the right conditions. While this explanation seems straightforward, it doesn't fully address the deeper question of why the constants of nature have their particular values in the first place. The strong anthropic principle, on the other hand, suggests that the universe must have properties that allow life to develop, implying some intrinsic connection between the cosmos and consciousness. This interpretation veers into more speculative territory, raising philosophical and even theological questions about purpose and design. The paradox becomes even more intriguing when we consider the multiverse hypothesis. If countless universes exist, each with its own set of physical constants, then it's not surprising that at least one of them would have the right conditions for life. In this view, our universe is simply one of the lucky ones, a cosmic lottery winner in a multiverse of possibilities. This idea resolves the fine-tuning problem without invoking design, but shifts the focus to the question of why a multiverse exists at all. Another approach to the anthropic principle paradox comes from string theory, which predicts a vast landscape of possible universes, each corresponding to a different way that extra dimensions are compactified. This landscape could potentially include universes with wildly different physical laws, many of which would be inhospitable to life. Our universe, then, would occupy a tiny, life-permitting niche within this vast landscape. Yet the fine-tuning debate isn't confined to theoretical physics. It also intersects with biology, chemistry, and planetary science. For instance, Earth's position in the solar system, within the habitable zone where liquid water can exist, seems remarkably suited for life. Our planet's magnetic field shields us from harmful cosmic radiation, while its moon stabilizes its axial tilt, ensuring relatively stable climates. Are these features evidence of a finely tuned environment, or are they just a rare coincidence in a universe filled with countless worlds? Critics of the fine-tuning argument point out that it suffers from confirmation bias. We focus on the conditions that allow life as we know it, but ignore the possibility of other forms of life that could thrive under entirely different circumstances. For example, silicon-based life might exist in environments hostile to carbon-based organisms, or life could arise in exotic states of matter we can barely imagine. This broader perspective suggests that the universe might not be fine-tuned for life in general, but rather for the specific kind of life we represent. The anthropic principle also raises profound philosophical questions about the nature of reality. If the universe is fine-tuned for life, does that imply a designer or higher purpose? Some see this as evidence for a creator, while others argue that invoking design is unnecessary when natural processes can explain the same phenomena. The debate straddles the boundary between science and metaphysics, highlighting the limits of what we can know about the cosmos. Another layer of complexity comes from the role of quantum mechanics in shaping the universe. Some interpretations suggest that the act of observation itself influences reality, implying that conscious beings like us might play a role in selecting the universe we experience. This idea, while speculative, aligns with the participatory anthropic principle, which suggests that the universe requires observers to exist in some fundamental way. Despite its paradoxical nature, the anthropic principle has practical implications for science. It helps guide the search for exoplanets by identifying conditions likely to support life, and shapes our understanding of how complex systems emerge in the universe. By studying the factors that make life possible, we gain insights into the delicate interplay of physics, chemistry, and biology on cosmic scales. At its core, the anthropic principle paradox challenges us to confront the mystery of existence itself. Why does the universe have the properties it does? Is it a random coincidence, a necessity of nature, or something more profound? While the answers remain elusive, the questions themselves reveal the deep connection between humanity and the cosmos. As we ponder the paradox, we are reminded of our unique position in the universe, not as passive observers, but as participants in its unfolding story. Whether the universe is fine-tuned for life, or we are simply fortunate to exist in a life-permitting universe, the fact that we can ask these questions is a testament to the astonishing complexity and beauty of existence. The holographic universe paradox. Is reality a projection? Imagine holding a piece of holographic film. At first glance, it seems like a flat, two-dimensional surface. But when you shine a light through it, a three-dimensional image springs to life. Now imagine that the universe itself operates in a similar way, that all the richness of our three-dimensional experience is encoded on a distant, two-dimensional surface. This mind-bending idea forms the basis of the holographic universe paradox, which suggests that the reality we perceive might be a projection of deeper, hidden information. The concept of a holographic universe originates from theoretical physics and has gained traction over the past few decades. Its roots lie in black hole physics and string theory, where the paradoxical behavior of information in extreme conditions led to revolutionary insights about the nature of reality. The key question is, can the universe's vast complexity be reduced to information stored on a surface far beyond our perception? And if so, what does that mean for our understanding of space, time, and existence itself? The story begins with black holes, those enigmatic objects formed when massive stars collapse under their own gravity. Black holes have an event horizon, a boundary beyond which nothing, not even light, can escape. In the 1970s, Stephen Hawking discovered that black holes emit radiation due to quantum effects near the event horizon. This emission, known as Hawking radiation, implies that black holes lose mass over time and eventually evaporate. But this raises a troubling question. What happens to the information about the matter that falls into a black hole? In classical physics, information cannot be destroyed. It's a fundamental principle of the universe. Yet black holes seem to violate this rule, leading to the black hole information paradox. If a black hole evaporates completely, does the information it consumed vanish forever? Or could it be encoded on the event horizon, preserving it in some form? This latter idea led to the holographic principle, a groundbreaking concept proposed by physicists Gerard T. Hooft and Leonard Susskind. The holographic principle states that all the information contained within a volume of space can be represented on its boundary, a two-dimensional surface. In the context of black holes, this means that everything falling into the black hole could be encoded on its event horizon. But this idea has far-reaching implications beyond black holes. If it's true for a black hole, could the entire universe work the same way? Could our three-dimensional reality be a holographic projection of information encoded on a distant, cosmic boundary? To understand how this might work, let's explore string theory, a framework that attempts to unify quantum mechanics and general relativity. String theory suggests that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings operate in higher dimensional spaces, with some dimensions curled up in ways we cannot perceive. Within this framework, the holographic principle offers a way to describe the universe's behavior at both macroscopic and quantum scales, linking gravity, space-time, and information. One of the most compelling pieces of evidence for the holographic principle comes from the study of anti-de Sitter space, ADS, and conformal field theory, CFT. Known as the ADS/CFT correspondence, this discovery by physicist Juan Meldacena provides a mathematical relationship between a higher dimensional gravitational theory, ADS space, and a lower dimensional quantum field theory, CFT, on its boundary. In simpler terms, it suggests that a universe with gravity in 3 dimensions could be equivalent to a universe without gravity in 2 dimensions, with the latter encoding all the information of the former. But what does this mean for our everyday experience of reality? If the holographic principle applies to the universe we inhabit, then everything we perceive as 3-dimensional space, time, matter, might emerge from a 2-dimensional structure at the edge of the cosmos. This doesn't mean we're living in a literal hologram, like characters in a movie. Instead, it implies that the universe's deepest nature might be informational rather than physical, with space-time itself emerging from a network of underlying data. This idea challenges our most basic assumptions about reality. In classical physics, space and time are the stage on which the universe unfolds, unchanging and absolute. But the holographic principle suggests that space-time is not fundamental. It's a derived phenomenon, much like a 3-dimensional holographic image is derived from a 2-dimensional surface. This shift in perspective could revolutionize our understanding of the universe's origins, its structure, and its ultimate fate. The holographic universe paradox also raises profound philosophical questions. If reality is fundamentally informational, what does that say about our perception of the world? Are we experiencing a simulation of sorts, created by the projection of deeper truths? While this idea overlaps with popular notions like simulation theory, it differs in that it's rooted in the physics of space-time and information rather than external creators or programmers. Critics of the holographic principle point out that its application to the observable universe remains speculative. Most of the evidence comes from highly specific models, like ADS/CFT, which may not perfectly describe our universe. Additionally, the idea of a holographic universe challenges our ability to empirically test such claims. If the encoding of reality occurs on a boundary billions of light years away, how could we ever access or verify it? Despite these challenges, the holographic principle has practical implications for physics. It provides a potential pathway to understanding quantum gravity, the elusive theory that unites the quantum world with Einstein's relativity. By treating gravity as an emergent phenomenon arising from information, the holographic principle offers a fresh perspective on problems like black hole entropy, space-time singularities, and the nature of dark energy. Philosophically, the holographic universe paradox invites us to rethink what it means to exist. If reality is a projection of deeper information, then our experiences, memories, and identities might also be encoded in ways we cannot yet comprehend. This doesn't diminish their importance. In fact, it elevates them, suggesting that even the most fleeting moments are part of a vast, interconnected cosmic tapestry. So, is reality a projection? The holographic universe paradox doesn't provide definitive answers, but it opens the door to profound questions. As physicists explore the boundaries of knowledge, they're uncovering a universe far more intricate and mysterious than we ever imagined. A place where dimensions blur, information reigns supreme, and reality itself might be an illusion. The arrow of time paradox. Why does time flow forward? Imagine watching a film in reverse. A shattered glass reassembles, water flows uphill, and a burst of smoke returns to its source. While amusing, this scenario feels unnatural. Our daily lives are governed by the steady march of time, moving forward from past to present to future. But why does time flow in this direction? The arrow of time paradox challenges us to understand what gives time its apparent one-way direction, and why the universe seems to prefer it. At the heart of this paradox lies a tension between the laws of physics and the reality we experience. The fundamental equations of physics, those describing gravity, electromagnetism, and even quantum mechanics, are time-symmetric. This means they work equally well whether time moves forward or backward. In theory, a system governed by these laws should allow for a reverse sequence of events. Yet, in practice, we experience an irreversible forward flow of time. Why? The answer, at least partially, lies in the second law of thermodynamics. This law states that entropy, a measure of disorder or randomness in a system, tends to increase over time in a closed system. For example, when you break an egg, its components scatter into a higher entropy state, and the process is extremely unlikely to reverse. The second law gives time a preferred direction, known as the thermodynamic arrow of time. But while entropy explains the direction of processes we observe, it doesn't fully explain why the universe started with such low entropy in the first place, a critical element of the paradox. To understand this, we must go back to the beginning of the universe itself. The Big Bang marks the origin of space-time, a moment when the universe was extraordinarily hot, dense, and seemingly chaotic. Paradoxically, this early state is considered low entropy because matter and energy were distributed uniformly. Over billions of years, as the universe expanded, structures like galaxies, stars, and planets formed, increasing the overall entropy. The question remains, why did the universe begin in such a low entropy state, setting the arrow of time in motion? One possible explanation involves the dynamics of gravity. In the early universe, gravity pulled matter into clumps, forming stars and galaxies, creating order and structure in what appeared to be chaos. This gravitational clustering increases entropy, aligning with the forward flow of time. But why gravity should behave this way, or why the universe started in a state conducive to this process, is still a mystery. The paradox deepens when we consider the quantum realm. In quantum mechanics, the concept of time is even more enigmatic. A quantum system exists in a superposition of states until measured, at which point it collapses into a definite state. This process, governed by the Schrödinger equation, doesn't distinguish between forward and backward time. Yet, when we observe quantum phenomena, they seem to follow the thermodynamic arrow. This raises the question, does the arrow of time emerge from quantum processes, or does it impose itself on them? Some physicists suggest that the arrow of time might not be fundamental, but emergent, arising from the way we perceive and measure the universe. In this view, time's direction could be a byproduct of human consciousness and memory. We remember the past, not the future, because our brains process information in a way consistent with the second law of thermodynamics. But does this mean time's flow is an illusion, or does it point to deeper truths about the relationship between mind and matter? Another perspective comes from cosmology, where the arrow of time may be linked to the expansion of the universe. As the cosmos grows, it creates more space for entropy to increase, reinforcing the forward flow of time. But what if the universe were to stop expanding and begin contracting in a big crunch? Some theorists propose that time's arrow could reverse in such a scenario, leading to a universe where effects precede causes and entropy decreases. However, this idea remains speculative and highly contentious. The paradox also raises profound questions about time's role in the laws of physics. In general relativity, time is a dimension, much like space, and the fabric of space-time can bend and warp under the influence of gravity. This means that time's flow is not uniform. It speeds up near massive objects and slows down in strong gravitational fields, as demonstrated by GPS satellites and experiments near black holes. These distortions challenge our intuitive understanding of time as a constant, linear progression. In theoretical physics, some models suggest that time may not exist at the most fundamental level. Instead, time could be an emergent property of a deeper, timeless reality. This idea aligns with approaches like loop quantum gravity, which seeks to unify quantum mechanics and general relativity. In such frameworks, time's flow might arise from the relationships between events rather than an inherent property of the universe. The arrow of time paradox also touches on existential and philosophical questions. If time's flow is a consequence of entropy, what does that mean for the concept of free will? Are we merely passengers in a universe dictated by thermodynamic inevitabilities? Or do our choices shape the course of events? Furthermore, if the arrow of time defines our experience of existence, what would it mean to live in a timeless or time-reversed reality? These questions stretch the limits of human understanding, inviting us to explore not just the mechanics of time, but its meaning. Despite its complexities, the arrow of time paradox offers profound insights into the universe's nature. It bridges disciplines, connecting physics, cosmology, and philosophy, and challenges us to rethink fundamental concepts. Why does time flow forward? The answer might lie in the interplay between entropy, the quantum world, and our own perceptions, a reminder that the simplest questions often lead to the deepest mysteries. The cosmological constant paradox. Why is the universe's expansion accelerating? Imagine standing on the surface of a calm lake. You toss a stone, and the ripples spread outward, gradually slowing as they dissipate. Now picture the universe itself as this lake, with the Big Bang as the stone that set everything in motion. You'd expect the universe's expansion to slow over time, as gravity pulls matter back together. But instead, observations reveal that the universe's expansion is accelerating, as if some mysterious force is pushing it apart. This phenomenon, attributed to the cosmological constant, creates a profound paradox. What is driving this acceleration, and why is it happening now? The story of the cosmological constant begins with Albert Einstein, who introduced it in 1917 as a mathematical term in his equations of general relativity. At the time, the prevailing belief was that the universe was static and unchanging. However, Einstein's equations naturally predicted an expanding or contracting universe. So he added the cosmological constant, a kind of anti-gravity force, to balance the equations and keep the universe stable. When astronomer Edwin Hubble discovered in 1929 that the universe was expanding, Einstein dismissed the constant as his greatest blunder. For decades, scientists assumed the universe's expansion was slowing due to gravity. But in 1998, two independent teams of astronomers studying distant supernovae made a startling discovery. The expansion of the universe was accelerating. This unexpected result revived the cosmological constant, now reinterpreted as a property of space itself, and led to the concept of dark energy, a mysterious force thought to make up roughly 68% of the universe's total energy content. Here's where the paradox arises. The cosmological constant, as described in general relativity, represents the energy density of empty space, or the vacuum. According to quantum field theory, even a perfect vacuum isn't truly empty. It teems with fleeting particles and fluctuations, known as zero-point energy. However, when physicists calculate the expected energy density of the vacuum using quantum mechanics, the result is staggeringly larger than the observed value. This discrepancy, off by a factor of 1012010^1210120, is the largest in the history of science. Why is the cosmological constant so small, yet not zero? And why does its influence dominate the universe today, rather than in the distant past or future? One possible explanation is that the cosmological constant is not constant at all. Some theories propose that dark energy could arise from a dynamic field, often called quintessence, that changes over time. Unlike a fixed cosmological constant, quintessence could evolve, potentially explaining why its effects have become significant only in the relatively recent cosmic past. However, this idea introduces its own challenges, requiring additional assumptions about the nature and behavior of this hypothetical field. Another approach involves the multiverse. If countless universes exist, each with its own physical constants, then our universe might simply be one where the cosmological constant is small enough to allow galaxies, stars, and planets to form. This idea, known as the anthropic principle, suggests that we observe the universe as it is because only a universe with these conditions could support observers like us. While intriguing, this explanation raises philosophical questions about whether it's satisfying to attribute fundamental properties of our universe to sheer coincidence. The paradox deepens when we consider the implications of dark energy for the universe's fate. If the acceleration continues indefinitely, the cosmos will become increasingly cold, dark, and isolated, a scenario known as the Big Freeze. Galaxies will drift beyond each other's observable horizons, stars will burn out, and even black holes will eventually evaporate, leaving a featureless void. However, if dark energy's effects intensify over time, it could lead to a big rip, tearing apart galaxies, stars, and even atoms as space-time itself is ripped asunder. Despite these dramatic possibilities, the nature of dark energy and the cosmological constant remains one of the greatest mysteries in physics. It challenges our understanding of space-time, quantum mechanics, and the fundamental forces of nature. Some physicists speculate that solving the cosmological constant paradox could require a unified theory of quantum gravity, which would reconcile quantum mechanics with Einstein's relativity. Such a theory might reveal new insights into the structure of space-time and the origins of the universe. The cosmological constant also raises profound questions about the nature of nothingness. If the vacuum has energy, can it ever truly be empty? And if dark energy is an inherent property of space, does that mean the universe has a built-in tendency toward expansion? These questions touch on the very foundations of existence, challenging us to rethink the nature of reality. Philosophically, the cosmological constant paradox highlights the tension between humanity's desire for simplicity and the complexity of the cosmos. For centuries, scientists have sought elegant, unified explanations for the universe's behavior. Yet the cosmological constant defies such simplicity, suggesting that the universe might be governed by forces and processes we can scarcely imagine. Despite its challenges, the cosmological constant paradox has inspired a wealth of scientific exploration. Observatories like the James Webb Space Telescope and ground-based projects like the Dark Energy Survey are probing the universe's expansion with unprecedented precision. These efforts aim to map the influence of dark energy across cosmic history, potentially unlocking clues about its nature and origin. As we grapple with this paradox, we are reminded of the limits of human knowledge and the boundless potential for discovery. Why is the universe's expansion accelerating? The answer may lie in the interplay of quantum mechanics, cosmology, and the fundamental structure of space-time, a reminder that the universe, in all its vastness, remains full of mystery. Imagine you're holding a pair of dice. You roll one, and it lands on 6. Instantly, no matter where the other die is, in another room, on the moon, or even light years away, it also shows 6. There's no visible link between the two dice, yet their outcomes are mysteriously connected. This analogy captures the essence of quantum entanglement, a phenomenon so bizarre that Einstein famously dismissed it as spooky action at a distance. But how can particles remain connected across vast distances? And what does this reveal about the nature of reality? At the heart of quantum entanglement lies a paradox that challenges our understanding of space, time, and causality. When two particles become entangled, their states are intertwined, no matter how far apart they travel. Measuring the state of one particle instantly determines the state of the other, as if information travels between them faster than the speed of light. This defies Einstein's theory of relativity, which holds that nothing can exceed the speed of light. So, what's really happening? To understand entanglement, we must first explore the peculiar world of quantum mechanics. Unlike classical particles, which have definite properties, quantum particles exist in a superposition of states until measured. For example, an electron can spin both up and down simultaneously until its spin is observed. When two particles interact and become entangled, their properties become correlated. If one particle is measured to spin up, the other will spin down, and vice versa. The key mystery is that this correlation persists even when the particles are separated by vast distances. This phenomenon was famously tested in the 1960s by physicist John Bell, who devised a way to experimentally distinguish between quantum mechanics and classical theories. Bell's theorem showed that if the universe were governed by local realism, the idea that particles have predetermined properties and that information cannot travel faster than light, then certain statistical patterns would hold in experiments. However, repeated tests have shown that quantum mechanics prevails, and entangled particles behave in ways that defy local realism. So, how does entanglement work? One interpretation is that the particles are not truly separate, but part of a single quantum system, even when spatially distant. In this view, the act of measuring one particle doesn't send information to the other. Instead, it reveals a property of the entire system. This perspective aligns with the idea of non-locality, which suggests that quantum mechanics transcends classical notions of space and time. Another interpretation is the many-worlds theory, which posits that every possible outcome of a quantum event occurs in a separate, parallel universe. When you measure one entangled particle, you and the particle branch into a universe where that specific outcome is realized. The other particle's measurement outcome is consistent because it occurs in the same branch. While this idea eliminates the need for faster-than-light communication, it raises profound questions about the nature of reality and the existence of parallel universes. Quantum entanglement also raises questions about the flow of information. Does one particle know the state of the other? If so, how does this happen instantaneously? Some physicists propose that the particles share a hidden connection encoded in their shared quantum state, rather than transmitting information in the traditional sense. Others suggest that our classical understanding of causality, where events are linked by cause and effect, might not apply in the quantum realm. The implications of quantum entanglement extend far beyond theoretical physics. In recent decades, researchers have harnessed entanglement to develop groundbreaking technologies, including quantum computing and quantum cryptography. Quantum computers leverage entanglement to perform calculations at speeds far beyond classical machines, while quantum cryptography offers virtually unbreakable security by detecting any attempt to eavesdrop on an entangled communication channel. Entanglement also plays a central role in efforts to unify quantum mechanics with general relativity. Some theorists suggest that space-time itself might emerge from the intricate web of quantum entanglement. This idea, known as holographic space-time, posits that the geometry of the universe could be a manifestation of entangled quantum information, a radical shift in our understanding of the fabric of reality. Despite its successes, quantum entanglement remains deeply mysterious. Does it imply that the universe is fundamentally interconnected, with no true separation between distant objects? If so, what does that mean for our understanding of individuality, locality, and the nature of existence? These questions touch on both scientific and philosophical territory, inviting us to rethink our assumptions about the universe. Experiments continue to push the boundaries of entanglement. In 2015, physicists conducted a cosmic bell test, using light from distant stars to determine the measurement settings for entangled particles. This ingenious approach aimed to close potential loopholes in earlier experiments, further confirming the reality of entanglement. As technology advances, researchers hope to test entanglement over even larger distances, perhaps using satellites or deep space probes. The quantum entanglement paradox challenges us to confront the strangeness of the quantum world. How can particles be connected across vast distances? The answer lies in a realm where intuition falters, and the familiar rules of classical physics give way to the profound interconnectedness of quantum reality. Entanglement reminds us that the universe is far more intricate, mysterious, and unified than we ever imagined, a place where even the smallest particles are bound by invisible threads of connection. The Boltzmann brain paradox. Could the universe be a fluke of consciousness? Imagine you're floating alone in the void of space. Suddenly, you gain full awareness. Your thoughts, memories, and sensations spring into existence spontaneously, with no history, no context, and no surroundings. This scenario might sound absurd, but it's a central idea in the Boltzmann brain paradox, a thought experiment that challenges our understanding of existence, consciousness, and the nature of the universe. Could our reality, and even our sense of self, be a fleeting, random occurrence in the vastness of space-time? The paradox is named after Ludwig Boltzmann, a 19th-century physicist who pioneered statistical mechanics and thermodynamics. Boltzmann proposed that the universe's apparent order and complexity could arise from random fluctuations in a chaotic, high-entropy system. In a sufficiently large and eternal cosmos, these fluctuations could occasionally create regions of low entropy, like the orderly structures we see around us: stars, galaxies, and even sentient beings. Here's where the paradox emerges. If the universe is infinite and eternal, as Boltzmann suggested, it's statistically more likely for a single, conscious brain to spontaneously form out of random quantum or thermal fluctuations than for an entire universe as intricate as ours to arise. These hypothetical Boltzmann brains would exist for a brief moment, fully aware but utterly isolated, before dissolving back into the chaos. If this logic holds, why do we perceive ourselves as part of a vast, coherent universe instead of fleeting, disembodied minds? To resolve this paradox, we must consider the nature of entropy. The second law of thermodynamics states that entropy tends to increase in a closed system, leading to a state of maximum disorder. The observable universe, however, began in a state of remarkably low entropy, a fact that underpins the arrow of time and the evolution of complex structures. But why did the universe start this way? If high-entropy states are vastly more probable, why didn't the cosmos begin in a chaotic equilibrium, making Boltzmann brains the norm? One explanation lies in the Big Bang and the subsequent expansion of the universe. The early universe's uniformity and low entropy set the stage for gravitational clustering, star formation, and the emergence of life. Some theorists suggest that the conditions of the Big Bang were fine-tuned to create a universe capable of evolving complexity. However, this raises further questions. Why would the universe be fine-tuned in the first place? And what determined its initial conditions? The anthropic principle offers another perspective. According to this view, we observe a universe conducive to life and consciousness because only in such a universe could observers exist to ask these questions. In other words, our existence biases our perception of reality, making it unsurprising that we find ourselves in an orderly, life-supporting cosmos rather than a chaotic void filled with Boltzmann brains. Yet, the paradox persists in theoretical models where the universe is eternal or part of a multiverse. In these scenarios, Boltzmann brains could outnumber ordinary observers like us by an unimaginable margin. If this were true, we'd face a philosophical dilemma. How can we trust our perceptions and memories if they might be the fleeting products of random fluctuations? Could everything we know and experience be an illusion, with no external reality to anchor it? To address these concerns, some physicists argue that the Boltzmann brain paradox reveals flaws in the assumption of an eternal universe. Models like the Big Bounce, which envision cycles of expansion and contraction, or the inflationary multiverse, where new universes constantly bud off from a primordial sea, might prevent the dominance of Boltzmann brains by resetting the cosmic conditions. Alternatively, the universe might have a finite lifespan, with entropy increasing until all activity ceases, leaving no room for random fluctuations. Quantum mechanics adds another layer of complexity. In the quantum realm, particles and fields can exist in superpositions, and their behavior is governed by probabilities rather than certainties. Some interpretations suggest that consciousness itself might play a role in collapsing quantum states, raising the question: could consciousness be a fundamental aspect of reality, rather than a byproduct of physical processes? If so, the Boltzmann brain paradox might point to deeper connections between mind and matter. Philosophically, the paradox challenges our understanding of identity and existence. What defines a conscious being? A brain, a body, or a lifetime of experiences? If a Boltzmann brain arises with a complete set of memories, is it any less real than a person who has lived a full life? These questions touch on the nature of selfhood, raising profound implications for fields like neuroscience, artificial intelligence, and ethics. The Boltzmann brain paradox also highlights the limits of human intuition. Our everyday experiences are shaped by finite timescales and familiar patterns, making it difficult to grasp the statistical and conceptual vastness of the universe. The paradox forces us to confront the possibility that reality might be far stranger and far less certain than we imagine. Despite its unsettling implications, the paradox inspires scientific and philosophical inquiry. By exploring the conditions that allow for consciousness, complexity, and order, we deepen our understanding of the universe and our place within it. Whether or not Boltzmann brains are a serious concern, their paradoxical nature reminds us of the value of questioning our assumptions and seeking ever greater clarity about the mysteries of existence. So, could the universe be a fluke of consciousness? The Boltzmann brain paradox doesn't offer easy answers, but it compels us to grapple with the nature of reality, the origins of order, and the profound mystery of our own awareness. A journey as vast and intricate as the cosmos itself. The Planck scale paradox. What happens at the smallest scales of reality? Imagine shrinking yourself down to explore the universe at its most fundamental level. You pass through atoms, zoom into protons and neutrons, and delve further still, reaching the smallest conceivable scale, the Planck scale. Here, at distances of about 10⁻35 10⁻35, 10⁻35 meters, and times as short as 10⁻43 10⁻43, 10⁻43 seconds, the very fabric of reality begins to break down. Space and time, as we understand them, lose their meaning, and quantum uncertainty reigns supreme. The Planck scale paradox asks, what happens at these unimaginably small scales, and how can we reconcile our understanding of physics at this limit? The Planck scale is named after Max Planck, the father of quantum theory, who first proposed it as a natural limit to measurements. It's defined using three fundamental constants: the speed of light, CCC, the gravitational constant, GGG, and Planck's constant, HHH. Together, these constants create a framework where quantum mechanics and general relativity, the two pillars of modern physics, collide. At larger scales, these theories coexist successfully. Quantum mechanics describes the behavior of particles and forces on microscopic scales, while general relativity explains the curvature of space-time caused by massive objects. But at the Planck scale, their equations produce contradictions, revealing gaps in our understanding. For example, general relativity treats space-time as continuous and smooth, while quantum mechanics suggests that energy, momentum, and even space-time itself are quantized. Reconciling these two frameworks is one of the greatest challenges in physics. One of the central mysteries of the Planck scale is the nature of space-time. At this limit, space-time might not be a smooth continuum, but instead consist of discrete, granular units, a concept often referred to as quantum foam. This foam is thought to be a chaotic, fluctuating sea of tiny space-time units, where distances and durations are no longer well-defined. Events at this scale are governed by extreme quantum uncertainty, with particles and fields popping in and out of existence. Another paradox emerges when we consider black holes. At the Planck scale, the effects of gravity become incredibly strong, even for tiny masses. Theoretical calculations suggest that any concentration of energy at this scale would collapse into a black hole, creating a space-time singularity. But what does this mean for the particles and forces we observe? Could the Planck scale represent a fundamental barrier to our understanding of physics, beyond which our current theories are entirely inadequate? The Planck scale also raises profound questions about the limits of measurement. To probe smaller scales, we need higher energies. But at Planck scale energies, the creation of black holes would prevent us from observing anything beyond. This creates a fundamental limit to what we can empirically investigate, leaving the Planck scale shrouded in mystery. Theoretical approaches to the Planck scale often involve attempts to unify quantum mechanics and general relativity into a single framework: quantum gravity. One leading candidate is string theory, which posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings operate at the Planck scale, and their vibrations determine the properties of particles and forces. String theory also introduces the concept of extra dimensions, beyond the familiar three of space and one of time, which are compactified at scales too small to observe. Another approach is loop quantum gravity, which suggests that space-time itself is quantized. In this theory, space-time is composed of discrete loops, much like a woven fabric. These loops form a network, called a spin network, which defines the geometry of the universe at the smallest scales. Unlike string theory, loop quantum gravity doesn't require extra dimensions and focuses on the quantization of spacetime alone. The Planck scale also intersects with ideas about the origins of the universe. The Big Bang, often described as the beginning of spacetime, reaches back to Planck scale conditions where our current understanding breaks down. Did the universe emerge from a quantum fluctuation? Was there something before the Big Bang? Or does the Planck scale represent a boundary beyond which time itself ceases to exist? These questions challenge not only physics but also our deepest philosophical assumptions about causality and existence. Interestingly, the Planck scale may hold the key to resolving other paradoxes, such as the black hole information paradox and the cosmological constant paradox. If space-time is quantized, the Planck scale might offer a framework to understand how information is preserved in black holes or why the energy density of the vacuum is so small. However, experimental evidence for these ideas remains elusive, as Planck scale phenomena are far beyond the reach of current technology. The Planck scale also invites speculation about the fundamental nature of reality. If space-time is granular, could the universe be a computational system, operating on discrete units of information? This idea aligns with the holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary. If true, the Planck scale might represent the smallest pixels of the cosmic hologram, revealing the universe as an intricate, emergent system. Philosophically, the Planck scale paradox forces us to confront the limits of human knowledge. Can we ever fully understand a realm so far removed from our everyday experience? Or is the Planck scale a natural boundary, beyond which the universe's workings remain forever hidden? These questions challenge not just physics, but the very nature of inquiry itself. Despite its mysteries, the Planck scale serves as a fertile ground for theoretical exploration, driving advancements in quantum gravity, cosmology, and particle physics. By probing the smallest scales of reality, we inch closer to answering some of the most profound questions about the universe's origins, structure, and ultimate fate. So, what happens at the smallest scales of reality? The Planck scale paradox doesn't provide definitive answers, but it reveals a cosmos rich with complexity, where the boundaries of space, time, and matter blur into a realm of infinite possibility. A reminder that even the smallest scales can hold the greatest mysteries. The vacuum energy paradox. Why is there something rather than nothing? Imagine staring into the emptiness of space, not at stars or galaxies, but at the vast stretches of nothingness between them. At first glance, it may seem like true emptiness, devoid of matter, energy, and activity. But quantum physics tells us a different story. Even the vacuum of space teems with activity, filled with fleeting particles and fluctuations. This mysterious vacuum energy gives rise to one of the most profound questions in physics and philosophy. Why is there something rather than nothing? And how does the vacuum itself shape the universe? The vacuum energy paradox arises from the peculiar nature of quantum mechanics. In classical physics, a vacuum is truly empty, a void with no particles or forces. However, quantum theory reveals that even the most perfect vacuum is a seething cauldron of activity. Virtual particles continuously pop in and out of existence, and quantum fields fluctuate with energy, even in the absence of matter. These phenomena are not merely theoretical. They have measurable effects, such as the Casimir effect, where two closely spaced plates experience an attractive force due to vacuum fluctuations. This quantum activity contributes to the vacuum energy, a value that represents the energy density of empty space. According to Einstein's theory of general relativity, energy affects the curvature of space-time, so vacuum energy has profound implications for the universe's structure and evolution. The paradox emerges when we try to reconcile the calculated value of vacuum energy with observations of the cosmos. Theoretical calculations from quantum field theory predict an extraordinarily large vacuum energy, many orders of magnitude greater than what we observe. If this calculated value were correct, the universe would expand so rapidly that galaxies, stars, and planets could never form. Instead, astronomical measurements reveal a vacuum energy density consistent with the cosmological constant, which drives the universe's accelerated expansion, but is far smaller than quantum predictions. This discrepancy, often cited as 1012010*1210120, a staggering mismatch, represents the greatest failure in theoretical physics. To understand the paradox, we must delve into the interplay between quantum mechanics and general relativity. Quantum field theory treats the vacuum as a complex, fluctuating entity, while general relativity describes space-time as smooth and continuous. Bridging these two frameworks, unifying quantum mechanics and gravity, remains one of the greatest challenges in science. Could the vacuum energy paradox point toward a deeper theory of quantum gravity? One potential resolution lies in the multiverse hypothesis. If our universe is just one of many, each with its own physical constants, then the observed vacuum energy could be a product of cosmic selection. In this view, most universes might have vacuum energies too large or too small to support complex structures, while our universe exists in a Goldilocks zone where galaxies and life can emerge. While intriguing, this explanation raises philosophical questions. Is it satisfying to attribute the universe's properties to a multiverse we cannot directly observe? Another approach involves the anthropic principle, which suggests that we observe a universe with a small vacuum energy because only such a universe can support observers like us. This principle shifts the focus from why the vacuum energy is small to why we find ourselves in a universe where it happens to be small, a subtle but significant distinction. Quantum mechanics also hints at the possibility of deeper, hidden symmetries in nature. Some physicists propose that these symmetries could cancel out the enormous contributions to vacuum energy from quantum fluctuations, leaving a small residual value. Such a mechanism, if discovered, could provide a natural explanation for the observed cosmological constant. However, no definitive evidence for these symmetries has yet been found. The vacuum energy paradox also touches on the nature of nothingness. In philosophical terms, nothing is often conceptualized as the absence of anything: matter, energy, space, or time. But in physics, even the vacuum is not truly nothing. It is a dynamic, energetic entity governed by the laws of quantum mechanics. This raises profound questions. Can true nothingness exist? And if so, how did the universe emerge from it? One possibility is that the universe arose from a quantum fluctuation in a pre-existing vacuum. In this scenario, the Big Bang represents the transition from a quantum state of nothingness to the observable cosmos. This idea aligns with certain interpretations of quantum mechanics, where probabilities govern outcomes, and something can spontaneously arise from nothing without violating physical laws. However, this explanation shifts the question further back. What created the vacuum itself? Another perspective comes from string theory, which suggests that our universe might be one of many brains within a higher dimensional space. In this framework, the vacuum energy of our universe could result from interactions between brains or the compactification of extra dimensions. While speculative, these ideas provide a tantalizing glimpse into the potential structure of the multiverse and the origins of vacuum energy. The paradox also has profound implications for the universe's fate. If vacuum energy remains constant, the universe will continue expanding indefinitely, leading to a big freeze where galaxies drift apart, stars burn out, and entropy reaches its maximum. Alternatively, if vacuum energy changes over time, it could trigger a big rip, tearing apart space-time itself, or a big crunch, collapsing the universe back into a singularity. Understanding the vacuum's nature is key to predicting these outcomes. Philosophically, the vacuum energy paradox challenges our assumptions about existence and meaning. Why is there something rather than nothing? The question transcends science, touching on metaphysics, theology, and the human desire to understand our place in the cosmos. While physics seeks empirical answers, the paradox reminds us that some mysteries may lie beyond the reach of observation and calculation. Despite its unresolved nature, the vacuum energy paradox drives progress in both theoretical and experimental physics. From precision measurements of the cosmic microwave background to advances in quantum field theory, scientists continue to probe the vacuum's secrets, seeking to illuminate the forces that shape the universe. So, why is there something rather than nothing? The vacuum energy paradox reveals the profound complexity of this question, showing that even the emptiest spaces in the universe teem with mystery, activity, and possibility. In seeking to understand the vacuum, we are ultimately exploring the essence of existence itself. The fine-tuning paradox. Why is the universe perfectly balanced for life? Imagine walking into a control room filled with hundreds of dials, each one precisely set to create the conditions necessary for life. A slight adjustment to any dial, turning gravity just a fraction stronger or weaker, altering the charge of an electron, or changing the density of dark energy, would result in a universe inhospitable to stars, planets, and life as we know it. This remarkable precision raises a profound question. Why is the universe so finely tuned for life? The fine-tuning paradox invites us to explore whether this balance is a cosmic coincidence, the result of natural laws, or evidence of something deeper. The concept of fine-tuning stems from the observation that the universe's fundamental constants and physical laws appear to be just right to allow the formation of complex structures. These include the strength of gravity, the electromagnetic force, the masses of fundamental particles, and the rate of cosmic expansion. Slight deviations in these values would render the universe dramatically different. For example, if gravity were slightly stronger, stars would burn out too quickly, collapsing into black holes before planets could form. If the electromagnetic force were weaker, atoms would fail to bind, leaving a universe without molecules or chemistry. If the cosmological constant were larger, the universe's rapid expansion would prevent galaxies from forming, leaving only a cold, dark void. Such precise calibration raises the paradox. Is this fine-tuning an inevitable consequence of natural processes, or does it suggest intentional design? Natural laws or coincidence? One explanation for fine-tuning is that it's simply a consequence of the underlying laws of physics. In this view, the constants of nature may not be adjustable dials, but fixed values arising from deeper principles. For example, string theory suggests that the properties of particles and forces might emerge from the vibrations of tiny, one-dimensional strings. These vibrations, shaped by the geometry of extra dimensions, could determine the constants we observe. If this explanation holds, fine-tuning would be an intrinsic feature of the universe's structure, not a cosmic fluke. Alternatively, fine-tuning could be a result of sheer coincidence. In an infinite universe or multiverse, where countless regions or universes exist with different physical constants, some are bound to have the right conditions for life. In this scenario, our universe is simply one of the rare, lucky ones, and we happen to exist in it because only such a universe could support observers. This perspective aligns with the anthropic principle, which asserts that the universe's properties must be compatible with our existence, because we are here to observe it. While the multiverse provides a compelling framework, it also raises philosophical questions. Is it satisfying to attribute fine-tuning to chance within a multiverse we cannot directly observe? And if the multiverse exists, what set its laws in motion? These questions push the boundaries of science and philosophy, inviting speculation about the origins of all existence. The simulation hypothesis. Another intriguing explanation for fine-tuning is the simulation hypothesis, which suggests that the universe might be a simulated reality created by an advanced intelligence. In this framework, the fine-tuning of physical constants could reflect the programming choices of the simulation's creators, designed to produce a life-permitting cosmos. While this idea remains speculative, it raises fascinating questions about the nature of reality and our role within it. If we are living in a simulation, can we ever discern its true nature, or are we confined to observing the rules of the program? Theological interpretations. For many, fine-tuning is seen as evidence of a purposeful creator or designer. The universe's precision, they argue, reflects intentionality, much like a watch implies a watchmaker. This perspective aligns with religious and metaphysical views that see the cosmos as imbued with meaning and purpose. However, critics of this argument caution that invoking a designer risks halting further inquiry by attributing fine-tuning to an unknowable cause rather than seeking deeper scientific explanations. Challenges to fine-tuning. Despite its compelling nature, the fine-tuning argument is not without challenges. Some scientists question whether the constants of nature are truly independent or whether they are interdependent, governed by deeper physical laws that naturally produce life-permitting conditions. Others suggest that life might arise in ways we cannot yet imagine, thriving in universes with very different physical parameters. If this is true, fine-tuning might be less remarkable than it appears, reflecting our limited perspective rather than a universal truth. Philosophical implications. The fine-tuning paradox forces us to confront profound philosophical questions about existence and purpose. If the universe is fine-tuned for life, does that make life itself significant? Or is it simply a byproduct of physical processes? Are we central to the cosmos, or merely observers in a vast, indifferent system? These questions challenge our assumptions about meaning, inviting us to reflect on our place in a universe that seems simultaneously vast, indifferent, and intricately precise. Experimental approaches. While fine-tuning is largely a theoretical concept, scientists continue to seek experimental evidence that might illuminate its origins. Observations of the cosmic microwave background, the distribution of dark matter, and the behavior of fundamental particles could offer clues about why the universe is the way it is. Advanced simulations of alternate universes, where physical constants are varied, may also shed light on how sensitive the cosmos is to small changes. The paradox of significance. Ultimately, the fine-tuning paradox is as much about perspective as it is about physics. The same precise conditions that make life possible also highlight the fragility of existence. Why is the universe perfectly balanced for life? The answer may lie in the interplay of chance, necessity, and deeper principles we have yet to uncover. What remains clear is that this paradox compels us to explore not only the workings of the cosmos, but also the meaning we derive from its extraordinary precision. If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The information paradox. Can information ever be lost? Imagine throwing a book into a fire. As the flames consume the pages, it seems the information, every word, every thought, is destroyed. But according to the laws of physics, that information isn't truly lost. The arrangement of atoms in the smoke and ash still contains traces of the book's original state, even if it's practically impossible to reconstruct. This principle, that information is never truly destroyed, lies at the heart of the information paradox, a puzzle that challenges our understanding of the universe and the very nature of reality. The paradox becomes most striking when applied to black holes, the mysterious objects formed when massive stars collapse under their own gravity. Black holes have event horizons, boundaries beyond which nothing, not even light, can escape. Anything that crosses this boundary is seemingly lost forever, swallowed by the black hole's immense gravitational pull. But what happens to the information about the swallowed object? Is it erased, or does it persist in some form? The conflict between theories. The information paradox arises from a conflict between two pillars of modern physics: quantum mechanics and general relativity. Quantum mechanics asserts that information about a physical system cannot be destroyed. This principle, known as unitarity, is fundamental to the theory. If information could be lost, the predictability of physical laws would break down, undermining the very foundation of quantum theory. General relativity, on the other hand, predicts that any information crossing a black hole's event horizon is irretrievably lost, as it falls into the singularity at the black hole's core, a point of infinite density where space-time itself breaks down. The tension between these two principles creates the information paradox. If black holes can destroy information, they violate quantum mechanics. If they don't, they challenge our understanding of general relativity. Hawking radiation and the paradox. The paradox gained prominence in the 1970s when Stephen Hawking discovered that black holes are not completely black. Due to quantum effects near the event horizon, black holes emit a faint glow of radiation, now known as Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually evaporate entirely. But Hawking's calculations suggested that this radiation is random, carrying no information about the matter that fell into the black hole. If the black hole evaporates completely, the information appears to vanish, violating quantum mechanics. Hawking's discovery sparked a decades-long debate about the fate of information in black holes. If information is lost, it would force a fundamental revision of quantum theory. If it's preserved, it challenges our understanding of black holes and space-time. Possible resolutions. Several theories have been proposed to resolve the information paradox, each offering a unique perspective on the fate of information. 1. Holographic principle. One of the most compelling ideas is the holographic principle. which suggests that all the information about a black hole's interior is encoded on its event horizon. This two-dimensional surface acts like a hologram, containing the full description of the three-dimensional black hole. If true, this principle could preserve information even as the black hole evaporates, aligning with quantum mechanics. 2. Black hole complementarity. This theory posits that information is both reflected at the event horizon and passes into the black hole, depending on the observer's perspective. From the outside, an observer sees the information encoded on the horizon, while an infalling observer experiences the interior. This duality avoids contradictions, but raises philosophical questions about the nature of reality. 3. Firewall hypothesis. The firewall hypothesis suggests that the event horizon is not a smooth boundary, but a searing wall of high-energy particles that destroys anything crossing it. This would prevent information from reaching the singularity, preserving it in some form outside the black hole. However, this idea violates the equivalence principle of general relativity, which states that falling into a black hole should feel no different from floating in empty space. 4. Quantum remnants. Some physicists propose that black holes leave behind quantum remnants after evaporating, tiny, stable objects that retain all the information they consumed. While this idea avoids information loss, it raises questions about the nature and stability of these remnants. 5. Wormholes and entanglement. Recent theories suggest that black holes could be connected by wormholes, shortcuts through space-time that allow information to escape. This idea ties in a quantum entanglement, where particles remain linked even across vast distances. If black holes are entangled with their emitted radiation, the information might be preserved through these connections. Broader implications. The information paradox extends beyond black holes, challenging our understanding of the universe's fundamental laws. If information can be lost, it raises troubling questions about the predictability and consistency of physics. Are the laws of nature truly universal, or do they break down in extreme conditions? The paradox also touches on the origins and fate of the universe. Black holes, as objects that distort space-time and consume information, may hold clues to the nature of quantum gravity, a theory that unites quantum mechanics and general relativity. Resolving the information paradox could lead to breakthroughs in our understanding of space-time, singularities, and the Big Bang itself. Philosophical reflections. The paradox invites deep philosophical questions about the nature of information and reality. If information is fundamental, as quantum mechanics suggests, what does it mean for it to be preserved? Is it an abstract property of the universe, or does it have a physical existence? And if information about the past is always encoded in the present, does that imply a deterministic cosmos where nothing is ever truly lost? Experimental exploration. While the information paradox remains theoretical, advances in observational technology could offer indirect evidence. Projects like the Event Horizon Telescope, which captured the first image of a black hole shadow, provide insights into how black holes interact with their surroundings. Future experiments in quantum gravity and high-energy physics may further illuminate the mechanisms behind information preservation. The search for answers. As scientists probe the depths of quantum mechanics, relativity, and cosmology, the information paradox serves as a reminder of the universe's complexity. Can information ever be lost? The answer may reshape our understanding of physics, revealing new connections between the fabric of reality and the fundamental laws that govern it. The dark energy puzzle. What is pushing the universe apart? Imagine a cosmic tug-of-war. On one side, gravity pulls galaxies together, its unyielding grip trying to slow the universe's expansion. On the other side, an unseen force, dark energy, pushes everything apart, accelerating the expansion of the cosmos. This mysterious force, which dominates the energy content of the universe, raises one of the most profound questions in modern astrophysics. What is dark energy, and why is it causing the universe to expand at an ever-increasing rate? The dark energy puzzle emerged from a startling discovery in the late 1990s. Two independent teams of astronomers studying distant Type Ia supernovae, a type of exploding star used as a standard candle to measure cosmic distances, found that these supernovae were dimmer than expected. This observation indicated that the universe's expansion wasn't slowing down, as previously thought, but accelerating. The discovery earned a Nobel Prize in Physics in 2011 and transformed our understanding of the cosmos. Today, dark energy is thought to make up about 68% of the universe's total energy content, dwarfing the contributions of ordinary matter, 5%, and dark matter, 27%. Despite its dominance, dark energy remains one of the greatest mysteries in physics. Its nature, origin, and future effects are unknown, and its discovery has raised fundamental questions about the universe's structure and fate. Underscore. The role of the cosmological constant. The simplest explanation for dark energy is the cosmological constant, a term originally introduced by Albert Einstein in his equations of general relativity. The cosmological constant represents a uniform energy density inherent to space itself, often described as the energy of the vacuum. Unlike matter or radiation, which dilute as the universe expands, the cosmological constant remains constant, exerting a repulsive force that drives the acceleration of cosmic expansion. While the cosmological constant provides a mathematically elegant solution, it raises its own paradoxes. Quantum field theory, which governs the behavior of particles and fields, predicts a vacuum energy density vastly larger than what is observed. This discrepancy, off by a staggering factor of 10120120 is the largest mismatch between theory and observation in the history of science. Why is the cosmological constant so small, and why does it dominate the universe today? Underscore. Dynamic dark energy, quintessence, and beyond. An alternative explanation for dark energy is that it's not a constant, but a dynamic field that evolves over time. This idea, known as quintessence, envisions dark energy as a scalar field permeating the universe. Unlike the cosmological constant, which exerts a constant repulsive force, quintessence could vary in strength and influence across time and space. If dark energy is dynamic, its effects might diminish in the distant future, or it could grow stronger, dramatically altering the universe's fate. Quintessence introduces additional questions. What is the nature of this field? Does it interact with other forces or particles? And if so, how? While quintessence offers a more flexible framework, it requires new physics to explain the behavior of the field, making it more speculative than the cosmological constant. Underscore. Modified gravity and dark energy. Some physicists suggest that dark energy might not be a separate entity at all, but a sign that our understanding of gravity is incomplete. In this view, the observed acceleration of the universe's expansion could result from modifications to Einstein's theory of general relativity on large scales. These modified gravity theories, such as F, R, gravity or brane-world models, propose that the laws of gravity might change under certain conditions, mimicking the effects of dark energy. While intriguing, modified gravity theories face challenges in reconciling their predictions with existing observations, such as the distribution of galaxies and the behavior of cosmic structures. However, they offer a promising avenue for exploring the interplay between dark energy and the geometry of space-time. Observational evidence and challenges. Despite its elusiveness, dark energy leaves measurable imprints on the universe. These include cosmic microwave background, CMB. The faint afterglow of the Big Bang carries subtle signatures of dark energy's influence on the universe's expansion history. Large-scale structure. The distribution of galaxies and galaxy clusters reflects the competition between gravity and dark energy over cosmic timescales. Baryon acoustic oscillations, BAOs. These ripples in the distribution of matter caused by sound waves in the early universe, provide a standard ruler for measuring the effects of dark energy. Ongoing and future surveys, such as the Euclid mission, the Dark Energy Spectroscopic Instrument, DESI, and the James Webb Space Telescope, JWST, aim to map the universe's expansion with unprecedented precision, shedding light on the nature of dark energy. The universe's fate. Dark energy holds the key to the universe's ultimate destiny. If its effects remain constant, the cosmos will continue to expand indefinitely, leading to a big freeze where galaxies drift apart, stars burn out, and matter decays into a dark, cold void. Alternatively, if dark energy grows stronger, it could cause a big rip, tearing apart galaxies, stars, and even atoms as space-time itself is pulled apart. Conversely, if dark energy weakens or reverses, gravity could regain dominance, leading to a big crunch where the universe collapses back into a singularity. These scenarios highlight the profound impact of dark energy on the evolution of the cosmos, emphasizing the need to understand its nature. Philosophical implications. The dark energy puzzle raises deep philosophical questions. Why does dark energy exist at all? Is it a fundamental property of the universe, or a temporary phenomenon tied to our particular epoch? The discovery of dark energy challenges the notion of a static, unchanging cosmos, revealing a dynamic, ever-evolving universe shaped by forces we barely understand. Toward a solution. Resolving the dark energy puzzle will require a synthesis of theoretical innovation and observational precision. Advances in quantum gravity, string theory, and cosmology may uncover the underlying principles driving cosmic acceleration. Meanwhile, experiments probing the behavior of quantum fields, particles, and space-time could reveal new insights into the nature of the vacuum. The mystery of expansion. What is pushing the universe apart? The dark energy puzzle underscores the complexity and mystery of the cosmos, reminding us that even as we expand our knowledge, the universe continues to surprise us. Dark energy is not just a force. It's a window into the profound interconnectedness of space, time, and existence. A reminder that the universe's greatest secrets often lie in the spaces between. The infinite universe paradox. Can something truly be infinite? Imagine standing at the edge of a vast plain that stretches endlessly in every direction. No matter how far you walk, the horizon remains out of reach. Now, scale this idea to the cosmos. Could the universe itself be infinite, with no boundaries, no edges, and no end? The infinite universe paradox challenges our understanding of space, time, and existence itself, forcing us to confront the profound question: can something truly be infinite? The idea of an infinite universe. The concept of an infinite universe has deep roots in both science and philosophy. Ancient philosophers like Anaximander and Giordano Bruno speculated that the cosmos might be boundless, containing countless stars and worlds. In modern cosmology, the question of whether the universe is infinite arises naturally from our understanding of space-time and the Big Bang. Cosmologists describe the universe using the framework of general relativity, where the shape and size of the cosmos depend on its total energy density. Observations of the cosmic microwave background, CMB, suggest that the universe is flat, or nearly so, on large scales. A flat universe is consistent with both an infinite cosmos and a very large but finite one. So, is the universe truly infinite, or does it just appear vast enough to seem so? The challenges of infinity. Infinity is not just a mathematical abstraction. It's a concept that strains human comprehension. To grasp the paradox of infinity, consider the following. 1. Infinite space. If the universe is infinite, it must contain an infinite number of galaxies, stars, and planets. In such a cosmos, every possible configuration of matter would exist somewhere, including exact duplicates of Earth, you and everyone you know. This leads to the unsettling idea of a multiverse within an infinite universe, where infinite variations of reality coexist. 2. Infinite time. An infinite universe would likely imply infinite time, stretching both into the past and future. But how does this reconcile with the Big Bang, which marks a beginning? Could the universe have existed forever before the Big Bang, undergoing cycles of expansion and contraction? Or is time itself finite, with a definite start? 3. The problem of edges. If the universe is not infinite, it must have an edge or boundary. But what lies beyond that boundary? If the universe is a closed system, like the surface of a sphere, it might be finite but unbounded. Traveling in one direction would eventually bring you back to your starting point, much like circumnavigating the Earth. This concept challenges our linear, intuitive understanding of space. Infinity in physics and mathematics. In mathematics, infinity is a well-defined concept used to describe unending processes, such as the set of all natural numbers. However, in physics, infinity often signals a breakdown of a theory. Singularities, like those at the center of black holes, represent points of infinite density where our current understanding of physics collapses. Does the infinity of the universe represent a similar breakdown, or is it a fundamental feature of reality? Some models of the universe attempt to sidestep infinity. For example, finite but unbounded models. These describe the universe as a higher dimensional shape, like a hypersphere, that is finite in size but has no edges. Loop quantum gravity. This theory suggests that space-time is quantized, with the smallest possible scale, effectively eliminating the concept of infinite divisibility. The multiverse and infinity. The concept of a multiverse complicates the infinite universe paradox. If multiple or infinite universes exist, each with different physical constants and laws, does that render our universe one of countless possibilities? And if the multiverse itself is infinite, what does that mean for the nature of reality? Some theorists argue that the multiverse is an unavoidable consequence of inflation, the rapid expansion that occurred moments after the Big Bang, which could create bubbles of space-time, each its own universe. Underscore. Philosophical and existential questions. Infinity is not just a scientific question, but a deeply philosophical one. If the universe is infinite, does that make individual lives and events insignificant in the grand scheme? Or does infinity elevate the value of every moment as part of an endless tapestry of existence? Furthermore, the infinite universe paradox invites us to consider the nature of existence itself. Why does something exist at all? And why does it take the form it does? Observational evidence. Astronomers continue to explore the shape and size of the universe through observations of the CMB, large-scale galaxy surveys, and the behavior of distant objects. These studies help constrain models of the universe's geometry and expansion. While current evidence points to a flat and potentially infinite universe, the ultimate answer remains elusive. The mystery of infinity. Can something truly be infinite? The infinite universe paradox reveals the limits of our understanding and the vastness of our curiosity. Whether the universe is infinite or merely unimaginably large, its mysteries remind us that even the simplest questions, like the shape of space, can lead to profound discoveries. Infinity is not just a concept. It's a doorway to exploring the fundamental nature of existence itself. The infinite universe paradox. Can something truly be infinite? Imagine standing at the edge of a vast plain that stretches endlessly in every direction. No matter how far you walk, the horizon remains out of reach. Now, scale this idea to the cosmos. Could the universe itself be infinite, with no boundaries, no edges, and no end? The infinite universe paradox challenges our understanding of space, time, and existence itself, forcing us to confront the profound question: can something truly be infinite? The idea of an infinite universe. The concept of an infinite universe has deep roots in both science and philosophy. Ancient philosophers like Anaximander and Giordano Bruno speculated that the cosmos might be boundless, containing countless stars and worlds. In modern cosmology, the question of whether the universe is infinite arises naturally from our understanding of space-time and the Big Bang. Cosmologists describe the universe using the framework of general relativity, where the shape and size of the cosmos depend on its total energy density. Observations of the cosmic microwave background, CMB, suggest that the universe is flat, or nearly so, on large scales. A flat universe is consistent with both an infinite cosmos and a very large but finite one. So, is the universe truly infinite, or does it just appear vast enough to seem so? The challenges of infinity. Infinity is not just a mathematical abstraction. It's a concept that strains human comprehension. To grasp the paradox of infinity, consider the following. 1. Infinite space. If the universe is infinite, it must contain an infinite number of galaxies, stars, and planets. In such a cosmos, every possible configuration of matter would exist somewhere, including exact duplicates of Earth, you, and everyone you know. This leads to the unsettling idea of a multiverse within an infinite universe, where infinite variations of reality coexist. 2. Infinite time. An infinite universe would likely imply infinite time, stretching both into the past and future. But how does this reconcile with the Big Bang, which marks a beginning? Could the universe have existed forever before the Big Bang, undergoing cycles of expansion and contraction, or is time itself finite, with a definite start? 3. The problem of edges. If the universe is not infinite, it must have an edge or boundary. But what lies beyond that boundary? If the universe is a closed system, like the surface of a sphere, it might be finite but unbounded. Traveling in one direction would eventually bring you back to your starting point, much like circumnavigating the Earth. This concept challenges our linear, intuitive understanding of space. Infinity in physics and mathematics. In mathematics, infinity is a well-defined concept used to describe unending processes, such as the set of all natural numbers. However, in physics, infinity often signals a breakdown of a theory. Singularities, like those at the center of black holes, represent points of infinite density where our current understanding of physics collapses. Does the infinity of the universe represent a similar breakdown, or is it a fundamental feature of reality? Some models of the universe attempt to sidestep infinity. For example, finite but unbounded models. These describe the universe as a higher dimensional shape, like a hypersphere, that is finite in size but has no edges. Loop quantum gravity. This theory suggests that space-time is quantized, with the smallest possible scale, effectively eliminating the concept of infinite divisibility. The multiverse and infinity. The concept of a multiverse complicates the infinite universe paradox. If multiple or infinite universes exist, each with different physical constants and laws, does that render our universe one of countless possibilities? And if the multiverse itself is infinite, what does that mean for the nature of reality? Some theorists argue that the multiverse is an unavoidable consequence of inflation, the rapid expansion that occurred moments after the Big Bang, which could create bubbles of space-time, each its own universe. Philosophical and existential questions. Infinity is not just a scientific question, but a deeply philosophical one. If the universe is infinite, does that make individual lives and events insignificant in the grand scheme? Or does infinity elevate the value of every moment as part of an endless tapestry of existence? Furthermore, the infinite universe paradox invites us to consider the nature of existence itself. Why does something exist at all, and why does it take the form it does? Observational evidence. Astronomers continue to explore the shape and size of the universe through observations of the CMB, large-scale galaxy surveys, and the behavior of distant objects. These studies help constrain models of the universe's geometry and expansion. While current evidence points to a flat and potentially infinite universe, the ultimate answer remains elusive. The mystery of infinity. Can something truly be infinite? The infinite universe paradox reveals the limits of our understanding and the vastness of our curiosity. Whether the universe is infinite or merely unimaginably large, its mysteries remind us that even the simplest questions, like the shape of space, can lead to profound discoveries. Infinity is not just a concept. It's a doorway to exploring the fundamental nature of existence itself. The observer effect paradox. Does observation shape reality? Imagine you're in a dark room with a single light switch. Flipping the switch reveals the layout of the room, its furniture, and its boundaries. But what if the act of flipping the switch didn't just reveal the room, it created it? This is the essence of the observer effect paradox, a concept rooted in quantum mechanics that challenges our understanding of reality. It asks a profound question. Does the universe exist independently of observation, or does observation play a fundamental role in shaping it? The quantum observer effect. At the heart of the paradox lies the peculiar behavior of quantum particles, such as electrons and photons. Unlike classical objects, quantum particles exist in a superposition of states, meaning they can occupy multiple positions, velocities, or spins simultaneously. This probabilistic nature is described by the wave function, a mathematical representation of all possible states a particle can take. However, when a measurement or observation is made, the wave function collapses, forcing the particle into a definite state. For example, in the famous double-slit experiment, electrons fired at a barrier with two slits produce an interference pattern on a screen, suggesting wave-like behavior. But when a detector is placed to observe which slit each electron passes through, the interference pattern disappears, and the electrons behave like particles. The mere act of observation changes the outcome. This phenomenon raises the central question of the observer effect paradox. What role does observation play in determining reality? Is the wave function a physical entity that collapses upon measurement? Or is it a tool for predicting probabilities, with observation merely revealing a pre-existing state? Underscore Interpretations of quantum mechanics. The observer effect paradox has inspired multiple interpretations of quantum mechanics, each offering a different perspective on the nature of reality. 1. Copenhagen interpretation. Proposed by Niels Bohr, this view suggests that the wave function represents probabilities, not physical reality. Measurement collapses the wave function, determining the particle's state. In this interpretation, reality doesn't exist in a definite form until observed. 2. Many-worlds interpretation. Hugh Everett's many-worlds interpretation posits that all possible outcomes of a quantum event occur, but in separate, parallel universes. Observation doesn't collapse the wave function. Instead, it determines which branch of the multiverse we experience. This eliminates the need for collapse, but raises questions about the nature of these alternate realities. 3. Pilot wave theory, also known as de Broglie theory. This interpretation suggests that particles always have definite positions, guided by a pilot wave. Observation doesn't collapse the wave function, but reveals the particle's true state. This view reintroduces determinism to quantum mechanics, but requires hidden variables. 4. Quantum Bayesianism, QBism. This interpretation treats the wave function as a subjective representation of an observer's knowledge about a system. Observation updates this knowledge rather than altering reality itself. Each interpretation addresses the observer effect paradox differently, reflecting the philosophical and conceptual challenges posed by quantum mechanics. The role of consciousness. A controversial aspect of the observer effect paradox is the potential role of consciousness in quantum measurement. Some interpretations, such as the von Neumann-Wigner hypothesis, suggest that consciousness collapses the wave function, implying that observers play an active role in creating reality. This idea, while intriguing, is highly debated and lacks empirical evidence. Critics argue that measurement doesn't require consciousness. Any interaction with a measuring device or environment can collapse the wave function. For example, decoherence theory explains how a quantum system becomes entangled with its surroundings, effectively choosing a state without requiring a conscious observer. The implications beyond quantum mechanics. The observer effect paradox extends beyond the quantum realm, influencing fields like cosmology and philosophy. In cosmology, the anthropic principle suggests that the universe's properties must allow for observers to exist, as only an observer-filled universe can be observed. This raises the question, does the universe require observers to exist, or is observation a byproduct of its evolution? Philosophically, the paradox challenges our understanding of reality. If observation shapes reality, what does that mean for the nature of existence? Are we passive witnesses of an objective world, or active participants in its creation? These questions touch on the nature of perception, agency, and the boundaries between the subjective and objective. Experimental investigations. Scientists continue to explore the observer effect paradox through experiments designed to probe the boundary between quantum and classical worlds. Advanced versions of the double-slit experiment, quantum entanglement studies, and tests of wave function collapse aim to clarify the role of observation in quantum mechanics. One notable experiment is the delayed choice quantum eraser, which shows that decisions made after a particle has passed through a slit can retroactively influence its behavior, suggesting a deeper connection between observation and reality. Underscore toward a unified understanding. Resolving the observer effect paradox may require a deeper theory that unifies quantum mechanics and general relativity, providing a more comprehensive understanding of space-time and measurement. Such a theory might reveal whether observation plays a fundamental role in shaping the universe, or is simply a phenomenon emergent from underlying physical laws. Underscore. The mystery of observation. Does observation shape reality? The observer effect paradox reveals the profound interconnectedness of knowledge, perception, and existence. It challenges us to rethink the nature of reality and our role within it, reminding us that the universe, at its most fundamental level, is both mysterious and intimately tied to the act of observation. The cosmological coincidence paradox. Why is the universe's expansion accelerating now? Imagine watching the hands of a cosmic clock ticking away the epochs of the universe. For billions of years, gravity has dominated, slowing the universe's expansion. But at this precise moment in cosmic history, something extraordinary is happening. The expansion is accelerating, driven by a mysterious force called dark energy. This phenomenon raises one of the most perplexing questions in cosmology. Why is the acceleration occurring now, billions of years after the Big Bang, and not in the distant past or future? This timing is at the heart of the cosmological coincidence paradox. The nature of the paradox. The paradox emerges from the interplay between the universe's key components. 1. Ordinary matter, 5%. This includes everything we can see and touch: stars, planets, galaxies, and us. 2. Dark matter, 27%. A mysterious form of matter that doesn't interact with light but exerts gravitational influence, holding galaxies together. 3. Dark energy, 68%. A force driving the universe's accelerated expansion, whose nature remains largely unknown. In the early universe, ordinary and dark matter dominated, providing the gravitational pull to slow the cosmic expansion. Dark energy, which acts as a repulsive force, was negligible. Over time, as the universe expanded and matter became more dilute, dark energy began to dominate. Today, dark energy and matter contribute roughly equally to the universe's total energy density, a fleeting balance in cosmic terms. This coincidence raises the question: why do we live in an era where the effects of dark energy are observable? Billions of years earlier, dark energy would have been too weak to influence expansion significantly, and billions of years later, its dominance would have erased the evidence of matter's role. Is this timing a mere accident, or does it point to deeper principles at work? Theoretical explanations. Several theories attempt to address the cosmological coincidence paradox, each with unique implications for our understanding of dark energy and the universe. 1. Anthropic principle. The anthropic principle suggests that we observe the universe at this specific moment, because only during this era can observers like us exist. Complex structures like galaxies, stars, and planets require billions of years to form, but if dark energy's dominance began much earlier, these structures might never have emerged. This explanation ties our existence to the universe's current balance, but leaves the underlying cause of the timing unexplained. 2. Quintessence. Quintessence posits that dark energy is not a constant, but a dynamic field that evolves over time. In this scenario, dark energy's influence could wax and wane, with its dominance at this moment being part of a natural cycle. However, this theory requires fine-tuning to explain why we're observing the transition precisely now. 3. Modified gravity. Some theories suggest that the effects attributed to dark energy arise from modifications to general relativity on large scales. In this view, the apparent coincidence might result from our incomplete understanding of gravity and its role in the universe's evolution. 4. Eternal inflation and the multiverse. In a multiverse framework where countless universes exist with different physical constants and properties, our universe might be one where dark energy and matter happen to balance at this moment. This explanation shifts the question to why our universe has these particular properties among the multiverse's possibilities. Observational challenges. Understanding the timing of cosmic acceleration requires precise measurements of the universe's expansion history and the behavior of dark energy. Key tools include supernovae as standard candles. Observing distant Type Ia supernovae helps map how the universe's expansion has changed over time. Baryon acoustic oscillations (BEOs). These large-scale patterns in the distribution of galaxies serve as a cosmic ruler for measuring expansion. Cosmic microwave background (CMB). The CMB provides a snapshot of the early universe, offering clues about the initial conditions that shaped cosmic evolution. Future missions, such as the Euclid Telescope, the Nancy Grace Roman Space Telescope, and the Dark Energy Spectroscopic Instrument, DESI, aim to refine our understanding of dark energy and its role in cosmic history. Philosophical implications. The cosmological coincidence paradox raises profound questions about the nature of the universe and our place within it. Is the timing of cosmic acceleration a mere accident, or does it reflect deeper truths about the cosmos? If dark energy is tied to the universe's fabric, does its behavior encode information about the origins and fate of spacetime itself? Moreover, the paradox invites reflection on the concept of coincidence in science. While scientists often seek deterministic explanations, some phenomena might arise from statistical or probabilistic processes. Could the universe's current state be one of many possible outcomes in a chaotic and unpredictable cosmos? The universe's future. The timing of cosmic acceleration also has implications for the universe's destiny. If dark energy remains constant, the universe will expand forever, leading to a big freeze. If dark energy grows stronger, it could trigger a big rip, tearing apart galaxies, stars, and even atoms. Alternatively, if dark energy weakens or reverses, gravity might eventually halt the expansion, culminating in a big crunch. Understanding why acceleration began when it did could provide crucial insights into these scenarios, offering a glimpse into the universe's ultimate fate. The mystery of timing. Why is the universe's expansion accelerating now? The cosmological coincidence paradox underscores the complexity and interconnectedness of cosmic forces, revealing a universe that continues to surprise and challenge our understanding. Whether the timing reflects chance, deeper principles, or an incomplete theory, the quest to resolve this paradox pushes the boundaries of human knowledge, offering new perspectives on the nature of time, space, and existence. The grand unification paradox. Why can't we combine gravity and quantum mechanics? Imagine standing on a mountain, observing the vast landscape below. To your left, rivers and forests stretch endlessly, governed by the intricate rules of quantum mechanics, the theory that explains the behavior of particles on the smallest scales. To your right, mountains and valleys curve gently under the influence of gravity, described by Einstein's general relativity. These two frameworks are marvels of human ingenuity, each providing a precise understanding of its domain. Yet, as you try to draw a single map that unites these landscapes, contradictions emerge. This challenge lies at the heart of the grand unification paradox. Why can't we combine gravity and quantum mechanics into a single, coherent theory? The divide between quantum mechanics and general relativity. Quantum mechanics governs the behavior of particles and forces at microscopic scales, describing phenomena like superposition, entanglement, and wave-particle duality. General relativity, by contrast, explains gravity as the curvature of space-time caused by massive objects, working exceptionally well on macroscopic scales such as planets, stars, and galaxies. Despite their successes, these two theories are fundamentally incompatible. Quantum mechanics assumes a fixed space-time backdrop, treating particles and fields as existing within space-time. General relativity, on the other hand, treats space-time itself as dynamic and malleable, shaped by the presence of matter and energy. When applied to extreme conditions, such as the singularity at the center of a black hole or the earliest moments of the Big Bang, the equations of these theories break down, yielding infinities and contradictions. A unified framework, often referred to as quantum gravity, is essential to bridge this divide. The quest for quantum gravity. For decades, physicists have pursued a theory that unites quantum mechanics and general relativity. Key contenders include 1. String theory. String theory posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. Different vibrational modes of these strings correspond to different particles, including the hypothetical graviton, a quantum particle that mediates gravity. String theory also introduces extra dimensions of space, compactified so tightly that they are imperceptible. While elegant, string theory is highly complex and lacks direct experimental evidence. 2. Loop quantum gravity, LQG. LQG takes a different approach, proposing that space-time itself is quantized. In this theory, space-time is composed of discrete loops, forming a network called a spin network. These loops define the smallest possible scales of space and time, effectively eliminating the infinities that plague classical theories. 3. Emergent gravity. Some researchers propose that gravity is not a fundamental force but an emergent phenomenon, arising from the collective behavior of underlying quantum processes. This idea, inspired by concepts like thermodynamics and information theory, suggests that space-time and gravity might emerge from the quantum entanglement of particles. 4. Causal set theory. In this framework, space-time is discrete and made up of a series of events connected by causal relationships. This avoids the continuous nature of space-time in general relativity, which leads to singularities. Each of these approaches has strengths and weaknesses, and none has yet achieved the status of a fully validated theory of quantum gravity. Underscore the role of black holes. Black holes, where gravity is extreme and quantum effects become significant, serve as a natural laboratory for testing quantum gravity. The black hole information paradox, the question of whether information swallowed by a black hole is lost forever, illustrates the tension between quantum mechanics and general relativity. Resolving this paradox could reveal key insights into the nature of space-time and the interplay between gravity and quantum phenomena. The challenge of experimental evidence. One of the greatest obstacles to unifying gravity and quantum mechanics is the lack of direct experimental evidence. Quantum effects of gravity are expected to appear only at the Planck scale, 10⁻35 10⁻35 10⁻35 meters, far beyond the reach of current technology. Efforts to detect quantum gravitational effects include gravitational wave observatories. Facilities like LIGO and Virgo detect ripples in spacetime caused by massive events, such as black hole mergers. While these observations are rooted in classical general relativity, future experiments might reveal quantum corrections to gravitational waves. High-energy particle colliders. Experiments at facilities like the Large Hadron Collider, LHC, aim to probe physics beyond the Standard Model, potentially uncovering evidence of extra dimensions or new particles predicted by string theory. Cosmological observations. The cosmic microwave background and large-scale structure of the universe provide indirect clues about the interplay between quantum mechanics and gravity during the universe's earliest moments. Philosophical implications. The grand unification paradox challenges our understanding of the universe at its most fundamental level. If gravity and quantum mechanics resist unification, does that imply a deeper flaw in our assumptions about the nature of reality? Are space and time themselves emergent properties rather than fundamental entities? These questions touch on the boundaries between physics, metaphysics, and philosophy. Underscore. Toward a unified framework. While the unification of gravity and quantum mechanics remains elusive, progress continues. Advances in theoretical models, computational techniques, and experimental precision bring us closer to bridging the divide. Success in this endeavor would not only resolve long-standing paradoxes, but also open new avenues for understanding the origins, structure, and fate of the universe. Underscore. The unifying force. Why can't we combine gravity and quantum mechanics? The grand unification paradox reveals the profound complexity of the universe's fundamental forces and the limits of human understanding. Yet, it also highlights the power of curiosity and collaboration in pushing those limits. In the quest for unification, we may discover not only the true nature of gravity and quantum mechanics, but also new principles that redefine our view of reality itself. The Fermi paradox. Where is everybody? Imagine gazing up at the night sky, marveling at the sheer number of stars scattered across the cosmos. With billions of galaxies, each containing billions of stars, many of which host planets, it seems inevitable that intelligent life should exist elsewhere. Yet, despite decades of searching, we've found no definitive signs of extraterrestrial civilizations. This apparent contradiction between the high probability of alien life and the lack of evidence is known as the Fermi paradox, a puzzle that forces us to question our place in the universe and the nature of life itself. Underscore. The scale of the universe and the probability of life. The Fermi paradox begins with the Drake equation, a framework for estimating the number of advanced civilizations in the Milky Way capable of communication. The equation considers factors like the rate of star formation, the fraction of stars with planetary systems, the number of planets per star that could support life, the likelihood of life arising, evolving into intelligence, and developing technology. Even with conservative estimates, the vast number of stars and planets suggests that intelligent civilizations should be abundant. If so, why haven't we encountered any evidence of their existence? Underscore. Possible explanations for the Fermi paradox. The paradox has inspired a wide range of hypotheses, from scientific to philosophical to speculative. These explanations fall into several broad categories. 1. They're rare or non-existent. Life is rare. While simple life may be common, the leap to complex, intelligent life could be exceedingly rare due to specific and improbable conditions. The Great Filter, some catastrophic barrier, either before or after intelligence arises, prevents civilizations from reaching an advanced stage. This could be biological, e.g., life rarely evolves intelligence or self-inflicted, e.g., advanced civilizations destroy themselves through war or environmental collapse. 2. They're far away or hidden. Cosmic isolation. The galaxy is vast and interstellar distances are immense. Advanced civilizations might exist, but they are too far away for us to detect. Technological limitations. Our current methods of searching for extraterrestrial life, such as radio signals, might be too primitive to detect advanced civilizations using technologies beyond our comprehension. Deliberate silence. Alien civilizations may intentionally avoid broadcasting their presence, either for self-preservation or ethical reasons. 3. They've been here, but we didn't notice. Ancient visitation. Aliens might have visited Earth in the distant past, leaving traces that have since eroded or gone unnoticed. Subtle observers. Advanced civilizations could be observing us without interfering, much like we observe wildlife in natural habitats. This is often referred to as the zoo hypothesis, for we're not looking properly. Narrow focus. Our searches focus primarily on radio signals or certain wavelengths, potentially missing other forms of communication like lasers, neutrinos, or quantum entanglement. Ephemeral signals. Civilizations might only broadcast detectable signals for a brief period before transitioning to undetectable technologies. 5. They're different from us. Non-biological life. Advanced civilizations might transition to machine intelligence, operating in ways fundamentally different from biological beings. Alien motivations. Aliens might have goals, values, or behaviors incomprehensible to us, making them difficult to recognize or predict. Underscore. The Kardashev scale and civilizational types. The Kardashev scale classifies civilizations based on their energy use. Type 1. A civilization that harnesses all available energy on its home planet. Type 2. A civilization that harnesses the energy of its star, potentially using structures like Dyson spheres. Type 3. A civilization that harnesses the energy of its entire galaxy. Humanity is currently a Type 0 civilization, far from even the first level. Advanced civilizations might exist at higher levels, rendering their activities undetectable to us. Underscore. The search for extraterrestrial intelligence, SETI. The search for extraterrestrial intelligence, SETI, focuses on detecting signals from alien civilizations. Projects like the Breakthrough Listen initiative scan the skies for radio transmissions, while missions like Kepler and TESS search for habitable exoplanets. Despite these efforts, no definitive signals have been found. Some scientists suggest expanding the search to include technosignatures, such as evidence of megastructures, artificial light, or industrial pollution on distant planets. Underscore. Philosophical and existential implications. The Fermi paradox raises profound questions about humanity's place in the universe. Are we alone? If we are the only intelligent civilization, what responsibilities do we bear as the universe's sole observers? What is the nature of intelligence? If intelligent life is rare or self-destructive, what lessons can we learn to ensure our survival? Are there universal limits? Does the paradox reflect inherent constraints on communication, exploration, or longevity for advanced civilizations? Underscore. Toward resolving the paradox, advances in technology and exploration may one day resolve the Fermi paradox. The discovery of microbial life on Mars or Europa would confirm that life arises easily, increasing the odds of intelligent civilizations. Conversely, the continued absence of evidence might suggest that we are rare, or that the great filter lies ahead of us. The mystery of silence. Where's everybody? The Fermi paradox confronts us with the vastness of the cosmos and the limits of our understanding. Whether the answer lies in technological limitations, cosmic isolation, or existential risks, the search for extraterrestrial life is a journey as much about understanding ourselves as it is about finding others. In the silence of the stars, we are reminded of both the possibilities and the fragility of existence. If you liked the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.